So today we are going to talk about frequent pattern mining. What is frequent pattern mining is that the main goal of this frequent pattern mining is to find out similar items. For example, if you go for a shopping, so if you buy milk, there are high chances that you will also buy bread. There is high chances that you will also buy butter, right? So those kind of items are called as frequent pattern items. So if you look on the other side, if you buy a book, there is high chances that you can also buy a pencil as well as an eraser. So these are called as frequent pattern mining, frequent pattern items or frequent item sets. So basically, what this subject is all trying to do is improve the customer base or improve the customer experience to improve the sales. For example, if you go to Amazon, if you are trying to buy something, it also shows you the relevant items that you would also like to buy, right? So something that we have discussed earlier. So it is just like if you see something like if you know if you are trying to buy bananas, there are high chances that you will also buy some other sort of fruits, right? You will not only buy bananas. There are high chances that you will also buy apples. You will also buy um, some other fruits. So what markets will do is like they will analyze the customer's behavior based on the data that is available with them. Like there could be a number of customers, so many customers that have bought many things in the past. So they will store all the data, and in future they will, I mean, they use that data to predict what are customers likely to buy together. So that studying that and how they do that data collection is what we're going to do today. Like if you see this diagram over here, we see something like customers who bought this also will bought these items. So that is the relation that we are trying to find out. How we will find out that? We will use the previous data of the customers that are available with us. Okay, so how does that data looks like? How to predict what are the items that could be brought together is all what we're going to see today. So if you look at this, the main goal of frequent pattern mining is to identify patterns. So we identify the patterns using frequent pattern mining that frequently co-occur in a data set. For example, it helps discover set of products that customers often buy together in a supermarket. So when you keep to attract the customers, you have to keep all the items together at one place. Let's suppose I can improve my business this way. If I know someone, there is a high probability of buying apples when someone bought bananas. It is meaningful to place the apples in the same rack of bananas, right? If I place bananas here and if I place apples somewhere in the rack which is far away from this rack, there the probability, you are decreasing the probability of the customer purchasing something. So if you keep both the items together at the same place, the probability would increase. So that is all what how the business will be improved, right? If you actually know, like if someone is buying bananas, if you know there is high probability of buying apples, if you can create an offer such a way that if you buy bananas, the discount will be applied on apples so that the sales of the apples will be increased a lot. So that is how this data will be useful. So we collect all the data. Let's suppose if there are 10 customers who actually bought different products in the past, we capture all the data and store into a database. So that database typically looks like this. So this is transaction ID 1. With transaction ID 1, they have bought three items: bread, milk, and butter. With transaction 2, they have bought bread and milk. With transaction 3, there could be n number of transactions happened in the store, and the relevant items purchased in every transaction are stored as a table. Okay, this is called as transactional database. Using this transactional database, we will try to find out the relation between buying different items together. Okay, that the different ways that we actually do this is what we're going to see today. Okay, this is called as frequent pattern mining, and with this we can actually improve the sales of a business by recommending the relevant products to the customers. So the transactional database actually looks like this. This is called a space of transactions. All the transactions is called a space of transactions. So transaction database typically looks like this. It has transaction ID and the items brought together. So if you just look at this, the particular you know particular item, I mean transactional database, you will see that bread and milk are brought together more frequently, or bread and butter are also more brought more frequently. Like everything happened twice here. Bread and milk happened twice. Bread and butter happened twice, and milk and bread. Okay, milk and bread happened one time, something of that sort. We are trying to find out the relation between different items in the database. Okay, so what is transactional database? Transactional database is something, but a transactional database consists of set of transactions where each transaction contains a set of items. Each transaction is identified by a unique transaction ID. So each transaction is identified by a unique transaction ID. So this is the transaction ID of this particular transaction. In this transaction, the customer has bought three items, which is bread, milk, and butter. Okay, so the space of transaction is nothing but all the transactions is called as space of transaction. So we always use this transactional database to derive the relation between different items that customers usually bought. Okay, so and the next, these are different terminologies that we're going to learn now. We're going to go to the next, you know, we're going to the next slide. So the other key concept here is what is item set? Item set is a collection of one or more items. Item in the sense bread is an item, milk is an item, butter is an item. Item set means it is a collection of one or more items. The number of items in the item set determines its size. An item set with k items is called as k item set. It is simple, so it is self-explanatory. So item set is nothing but a collection of one or more items. The bread is item, milk is item, butter is item. Okay, so the number of items in the item set is determined by its size. Let's suppose if you see this particular item set, there's only one item. So it is called as one item set. If it has two items, it is called as two item set. If it has three items, it is called as three item set. So each item has to be unique in the transaction in the item set. So any combination, any collection of items is called as an item set. So each particular each one is called as item, and the combination of these is called as item set. So then depending on the number of items in this particular item set, it is named as k item set. If it has two items, it is called as two item set. If it has three items, it is called as three item set. So that is what actually item set means. So you have learned about transactional space or transactional database. The second one is item. Each product in the basket is called as an item. And the collection of items is called as, it can be one or more. The collection of items is called as item set. Depending on the size of the item set, we name it as k item set. Okay. So that is what item set is. Transactional database is this one, right? Transactional database is, this is called as transactional database. Each row will have transaction ID and the relevant items bought in the transaction. Okay. And then what is the next one? Item set space. Item set space in the sense, what are the possible item sets that can be formed by the set, right? A set of all possible item sets. Let's suppose if I was given with bread, milk, and butter, what are different combinations that we can create from this is what this basically means is. So it's simple, like it is as simple as like number of combinations that we can derive from the set of items that we do have. Let's suppose if he has A, B, C as three different items, the number of combinations that we can create from this. So now what are the number of combinations that we can create from these three items? It is something like this, right? 0 1 0 0 1 1 1 0 0 1 1 1. This means this is an empty set. No, nothing is chosen here. So here only C is chosen. The item C is only chosen. Here only the item B is chosen. Here B and C are chosen. Here only A is chosen. Here ABC is also chosen. So item set space is nothing but the total possible item sets that can be formed by the set of items that are given. So here with three items, we can form eight combinations, including the empty set, right? Here 100 is there, 101 is there, 110 will also be there. So this would be AC. This would be AC and this is AB. So these are the different combinations that we can create from the items that we do have, right? So technically, if we have n items, the total number of the items in the item space is 2 to the power of n, which is equal to 2 to the power of n. So right now we have taken three items. So the total number of combinations that we can create with these three items is 2 to the power of 3, which is equal to 8, right? So these are the 8 different combinations that we can create from the three items that are given to us. So all these items together are called as item set space. Okay. Item is a single product. Item set is the number of products in each transaction. Item set space means all the possible combinations that can be formed with those items is called as item set space. The total number of uh, possible subsets of the given a given number of items is 2 to the power of n, which is equal to, in this case we have taken three products, so the total number of uh, items in the item set space is equal to 8. Okay, and then we are talking about transactional identifier set. TID set is nothing but, let's suppose if you are given an item set. Okay, so this is an item set, bread and milk. What is transactional identifier set? TID is in which all transactions this combination has happened. Let's suppose if this is the transactional database that is given to you, and this is the item set that is given to you. So bread is an item, milk is an item, this is an item set. Item space is the possible combinations that we can create from bread and milk will be the item set space. Okay, if you are given only bread and milk, what are the combinations that you can create? One is empty set, one is bread, the third one is milk, and the fourth one is bread milk. What is transaction ID set means? Transaction ID set is nothing but in which all transactions this combination has happened. That set would be, the transaction ID set. Okay, so if you look at this bread and milk, okay, in which all transactions bread and milk has happened. In transaction one, you have bread and milk, so you have to take that now. So in one, bread and milk has happened. In transaction two, do you have bread and milk? Yes, you have bread and milk. In transaction 3, do you have bread and milk? No, you don't have, right? In transaction 4, you don't have. In transaction 5, you don't have. So TID set, transaction identifier set, is nothing but in which all transactions the item set has happened. That set would be the transaction ID set. Now for bread and milk, it is 1 and 2. Okay, so that is what transactional identifier set means. That is denoted by T of X. Okay, transaction ID set, identifier set, is denoted by T of X. Let's suppose if you are given milk and butter, if you are given with milk and butter, if X is given as milk and butter, what would be the transaction IDs? Milk and butter is given as an X, as an item set. Just remember the words item set. This is the item set. Milk and butter is an item set, which is a collection of one or more items. Each one is called as an item. Item set space means all the number of possible combinations that can be created by the items that are given to you. Okay, the possible number of items in an item set space is 2 to the power of n, where n is the number of items given to you. Okay, transaction identifier set is nothing but in which all transactions the item set has happened. That set would be called as transaction identifier set. If you take this example of milk and butter, in which all transactions it has happened. In transaction 1, it has happened. In transaction 2, it is not there. In transaction 3, it is there. Milk and butter is there. In fourth, it is not there. In fifth, it is not there. So the transaction ID set for milk and butter is 1 and 3. Okay. So that is what transaction identifier set means. Now, the next thing that you're going to learn, which is very important, is support. How to calculate the support of a particular item set. Support is nothing but the length of or the cardinality of the Tid set. It is just the modulus of Tid set. The length of the Tid set is called as the cardinality of Tid set is support. Okay. It's here we are just capturing all the transaction IDs when you say transaction ID set. But what support basically means, support is nothing but the total number of transactions in which that particular item set has happened. Okay, so it's a sum of the transaction IDs, or it is called as the length of the set or the cardinality of that set. Let's take this example. Okay, support of an item set is the number of transactions that contains that item set. In it is just nothing but number of transactions that contains that item set. What is the item set that is given here? Bread and milk is the item set that is given here. When you want to calculate support, you want to calculate the number of transactions in which this bread and milk is there. Okay, let's go calculate that. In transaction 1 you have bread and milk. In transaction 2 you have bread and milk. So you have two transactions now. In first transaction you have that, in second transaction you have that, in third transaction you don't have that, in fourth you don't have bread and milk, in fifth you don't have that. So the support would be equal to 2. Okay, similarly if you're given with bread and butter, let's calculate for bread and butter. What is the support of your, if you're asked with what is the support of bread and butter, you just have to go to every transaction and you have to calculate that. So bread and butter is there in first transaction, plus bread and butter is not there in the second one. In third one it's not there, in fourth one it is there, in fifth one it is not there. So it is 2 now. Okay, support is calculated as the number of transactions that contains that particular item set. Okay, you calculated for bread and milk, you also have calculated for bread and butter. Okay, and next thing is next comes there are two types of support. One is absolute support and the other one is relative support. What is absolute support? Absolute support is exactly the count that you have done. Okay, the number of transactions that contains that item set X. So 2 is the absolute support for bread and milk. 2 is the absolute support for bread and butter. And what is relative support means? Relative support means the number, it is compared with the total length of the transaction ID set. It is nothing but number of transactions contains that item set by total number of transactions. So for bread and milk, it would be equal to 2 by 5 because 2 is the count of transactions or number of transactions in which bread and milk has happened, and 5 is the total number of transactions. What is the length of this transaction? I mean transactional database, it is 5. So that is called as relative support of support 2 by 5. What is the relative support for bread and butter? It is 2 by 5. Absolute support is 2, relative support is 2 by 5. Relative support is how relatively it is frequent, okay, or frequent with respect to the total transactional database. Okay, so support is that is how you calculate the support. Okay, and now what is the item set mining problem? What is that you're trying to find out? Your main goal is to find out the frequent items that are happening in a basket so that you can improve your sales or you can improve your business. So everything that you're trying to find out is what are the relative items in an item set. Okay, let's suppose if as we discussed earlier, if someone is buying bananas, there is high probability that he will also go with other fruits like apple, pineapple, or oranges, right? He will go with other fruits. So you always have to find out that combination. If someone is buying something, what is the probability that the other products will also be brought? So that is exactly what you see in Amazon websites, right? So if you buy something, it will also recommend the relevant products that you wish to buy or a user wish to buy, so that the user may also add that particular recommended product to the cart, and the sales would be improved. So how do we actually do that is what It is. So your goal with the item set mining problem is you want to find out frequent item sets. What is called as frequent item sets, which is frequently happening in the transactional database. What are the products that are frequently bought by the users, right? That is what you are trying to find out. Find all frequent item sets in a transactional database that has support greater than or equal to the minimum support threshold. So if you say like, if the frequency, if I say, if you take this transactional database, if I say pick all the frequent item sets whose support is greater than or equal to 2, okay, that is your goal. You have to find out the frequently happening products in your transactional database given the minimum support threshold. So let's suppose if I decided to have the minimum support threshold as 2, it can also be the percentage. Let's suppose if I say 50 percentage, that means 50 percentage of the transactional database. What would be the 50% here? The number of transactions is 5, so 50% is 2.5. So we'll take 3 transactions as a threshold. It can be percentage, or it would be just the number of an integer number specifying the number of in number of transactions it has to happen. So that is the item set mining problem. So your main goal is to find out the frequent item sets, and it should have a threshold, right? So you cannot pick all the item sets, all the frequent item sets. If it is with a frequency of 1 or a support of 1, okay, frequency is nothing but the support. They're interchangeable terms. When you say frequency 1, you may not be interested in that. That could happen just with a random chance with one customer. What is your threshold? How do you want to pick the frequently happening items? You should have a threshold, right? Let's suppose in this case, as I just have 5 item sets, I can set my threshold as 50 percentage, or I can set my threshold as 2. If I set my threshold as 2, what does that mean? If any item set happening more than twice, if any combination of, if the frequent item sets is happening more than twice, I can consider that as an required item set, or the item set that I would like to find out. Okay, so that is what actually it means is. So what is the support of bread and milk here? Bread and milk is support is greater than or equal to 2. So that would be one of the combination that I would like to find out. Okay, and bread and butter also happen twice. That is also that is also my interest. So I know bread and butter is also a combination. What about milk and butter? Milk and butter also happen twice. Okay, so that is also my interest. Butter and eggs, that is also my interest because it also happened twice. But if I say the threshold as 3, if I set the threshold as 3, or the frequency minimum support threshold as 3, can you tell me what items would be picked now by the item set mining? So what items would you like to think as the frequently brought together if the minimum set threshold is set to 3? You have to find out the combination of item, if that is happening thrice or not. If you take bread and milk, it has happened just twice, so that would not be a frequent item set. If you take milk and butter, it also happened twice. That would not be a frequent item set. So if you say bread, butter and milk is there, butter and eggs, it happened just once. So you don't have any item set with which is satisfying that particular minimum support value. Okay, so that is how what there are 2 steps here. One step is to find out the combinations of the items. What is the maximum? What are all the items that you do have right now? Okay, to solve this problem, to solve this item set mining problem, what all you have to do is, these are the steps that you will perform. It's just like general thinking that you can just come up with. The item set mining problem says you have to find out all frequent item sets. That is the whole goal of this subject of this matter. Okay, you want to find out, you have all the transactions list of different customers. It could be in real world, it could be very huge, from which you will find out. But here for our understanding, we came up with just a simple transactional database with 5 transactions. right? What is your goal now? You have to find out frequent item sets in the transactional database. Which items together happen more frequently is your interest. That is what which you are using to improve your business or sales. Okay. What are those frequent item sets whose support or frequency is greater than minimum support that you have set? So frequent items that you are trying to find out frequent item sets whose support is greater than or equal to minimum support. Let's suppose you are trying to find out the support of a transaction whose support is greater than or equal to minimum support. Minimum support is something that you have that you will set. It could be the percentage of the number of transactions or some random value. I mean some value that you will set. Most probably it would be the percentage of number of transactions. If it is happening in more than 50% of the transactions, maybe that is your interest. You want to have a look at that and use that to improve your business. So that is all what item set mining problem is. To solve this problem, the basic solution that you will have is, what you will basically do is find out all the combinations of these items and then calculate the support of those. And then if the support of them is greater than a particular value, you will actually recommend those products, right? So when you derive the combinations, what would you think is the easiest way if you have n number of transactions? So that is what you're going to study in future, how to create. There are two steps. The first step is finding out all possible combinations. Find all possible item sets, I would say. What is item set? Item set is just nothing but the collection of items. So the first step would be find out all the possible item sets. Second step that you would perform is calculate the support of each item set, okay, that you have created, that you have derived. Calculate support of each item set. You know what is the support is and how do you calculate the support. Once you calculated the support of that, the third step is compare the support with the minimum support threshold. So if support of that item set is greater than threshold or minimum support, min sub, I would say, if it is greater than minimum support, in short, I call it as min sub, pick that item. If not, throw that item away. So if if it is less, throw that away. If it is greater than or equal to the minimum support value, this is your interest. This item set collection is your interest, or this item set is your interest. So that you can use that item set to recommend the products to the customers. Okay, that is what item set mining problem is. Okay, item collection problem. So this is an I of I, items common to all the transactions in Tid set. Okay, that is what I of Y says. So we have seen T of X. What is T of X? T of X is nothing but the transactional identifier set. That is what TID. We call this as Tid set, transactional identifier set. Similarly, you have another representation called as I of Y. What is I of Y? Y is again uh, the transactional set. Y is called as a transactional set. If a transactional set is given, when you want to find out I of I is nothing but the intersection of both the transactions. Okay, items, intersection of items in both the transactions. Let's suppose if you are given with 1 and 2, if you're given with transactions 1 and 2, what are the common items in this, or what is the intersection of the items of these two item sets? Bread and milk is the intersection. Okay, these two are common in both the transactions. So that is called as item sets common to all the transactions. Okay, Y is the TID set. That is what you pass to I. So which is items common. We call this as items common in transaction ID set. So that when you want to find out I of I is nothing but the items that are common in both the transactions. Here for transaction 1 and 2, the common items are bread and milk. So that then I of Y will become bread and milk. That is what I of Y is. So what you all have learned, you have learned what are frequent items. You have learned these are the frequent items, right? If one is buying milk, there is high chances that he will also buy butter. He will also buy, I mean, bread, butter. If a user or a customer is buying book, there is high chances that he will also buy pencil and eraser. So our goal with the data that is available with us is to find out these frequent items. What are all happening with together in a transactional database more frequently is what frequent mining all about is. So we have learned about transactional database. Transactional database is nothing but um, it's an tabular format where a transaction ID is associated with the item spot with that particular transaction, right? So in real world, it would be very huge, and out of that huge data, we are going to derive the frequent items, and we will learn all those methods in this frequent pattern mining. Okay, and then comes you learned about item set. Item set is nothing but a collection of one or more items. Item set space is the set of all possible combinations of the items. Items set of items, I mean to say, that can be found from a set of items, and the number of possible item sets in an item set space is 2 to the power of n. And you have learned about TID set, which is transactional identifier set. It is nothing but given an item set, you just have to find out in what all transactions that particular item set has happened. And then you calculated support. Support is of two types. One is relative support and the other one is absolute support. You also have seen the difference between them, and you also have understood what is item set mining problem. You just have to find out the item sets where support of the item set is greater than or equal to the minimum support. Your interest is to find out all such possible item sets, right? And then you also have find out what is I of I, where Y is the TID set. I of I is nothing but the intersection of all the items in all the transactions in the TID set. That is what I of I is. And now you want to understand what is closed item set. An item set is called as closed if it satisfies the condition that is given here. Okay. When you're asked to find out item set, closed item set, to say whether an item set is closed or not, this condition is what it needs to get satisfied. I of T of X, you already know how to calculate this. When given a transaction ID set, when given a TID set, when you apply I to it, it is nothing but the intersection of items in all the transactions present in the TID set. Okay, if I of I is given, that is called as I of I. Y is just nothing but the T of X in I of I, transaction ID set. If this is equal to X, okay, then that is called as closed. Okay, that item set is called as closed. Let's see an example now. Okay, given bread and milk, you're given with an item set which is bread and milk. Now the first step is to find out T of X. T of X is nothing but transaction ID set. Transaction ID set means in which all transactions bread and milk has happened is what T of X is. Okay, let's go back and see where in which all transactions you have bread and milk. So bread and milk is there in two transactions, 1 and 2. Okay, uh, that is 1 and 2, right? So if I go back here, transaction ID becomes 1 comma 2. Okay, and now you want to apply I on top of T of X. Okay, which is I of transaction ID set, which is 1 comma 2. So what is I of 1 comma 2? Which is the items that are common in both 1 and 2, right? So now what are the items that are common in 1 and 2? 1 and 2, the items common are bread and milk. Okay, so I would say this is bread and milk. The output is bread and milk if I apply I on top of it. So now this becomes equal to X. So if I of T of X is equal to X, then that becomes closed item set. Okay, such item sets are called as closed item sets. It has to satisfy this particular condition. Okay, the round trip has to be satisfied. I of T of X should be equal to X again. So if that is happening, so we are going from item set space to transaction set space, and transaction set space to space back to item set space. We are going from I to T. We are finding the transactions, and from the transaction set, we are coming back to the item set space. When both are equal, we call that as closed item set. Okay. That is what closed item sets means. We will again come back to closed item sets to understand more. Uh, that is an example of this. Okay. All right. Uh, right. So now you understood the goal, right? Given a data set, you want to find out all the possible item sets in this. Okay. So as I told you earlier, the first step given, we are talking about the naive approach. A blunt approach is what we are going to try first. So your goal is to find out all the possible item sets that are frequent, and that item set support has to be greater than or equal to the minimum support, or six. Here it is given as, here we are given with the minimum support as we are given with the minimum support as 3. We are given with the minimum support as 3, or minimum support as 60%. 60% of transactions 5 on V is 3, right? We have 5 transactions, 60% of that is 3. Okay. If we have 100 transactions, the 60% of that is 60, right? So if an item set is happening in more than, together, if an item set is happening in more than 60 transactions, we consider that as an required frequent item set. Okay, so that is all what we are trying to solve, and we see the best approach of solving that is what we will learn for in the next few slides. What is the best way to find out the frequent item sets given a transactional database? That is what we have to find out. Okay, so as I told you, the naive approach is frequent pattern mining, involves generating all possible item sets from a transactional database and checking their frequency against a user-defined minimum support threshold, which conceptually simple. This approach is computationally expensive and inefficient for large data sets. So this is the naive approach that we are doing. So the general thought here is, let's suppose if you're given with n items, okay, you want to find out what are the frequent item sets that are happening. How do you derive this? So if you just look at this, can you derive any frequent item sets from this? Can you say, just go, can you pick any two items AC? You can pick two items from here and go find out all the, if AC is present in any of the transactions or not, and then you can pick AD and find out if these two are the items that that form together in most of the databases or not. Okay, that is the way you find out. Pick up an item set, pick up a combination, and go through all the transactional database and find out in number of transactions that has happened. And if it is greater than 3, you mark that as an valid item set. Okay, or frequent pattern set. That is the approach that you do, right? That is the initial thought that we get, but that is computationally expensive. So your goal right now is to find out, the first goal of yours is to find out the frequently happening items, which is called as item set, frequent item sets. Let's suppose you have two products. Think of these as different products like milk, butter, and all that. To simplify this stuff, I just named it as A and C. But think of this as an items like butter and milk, or bread and milk, or something of that sort. Let's suppose I'm going to find out if AC is frequent or not, butter and milk is frequent or not. What I have to do, I have to take this item set, just two items. I want to go through all the transactions and find out if these two happened frequently or not. Okay, so AC doesn't happen in the second transaction, happen in the third transaction, fourth transaction, no, fifth transaction. The support of AC is 3. So AC is a valid combination. Okay, and the second combination that I come up with is AD, right? So I go find out if butter and bread is are frequent or not. Okay, that means when I say frequent, if user is buying bread, what is the chances that he is also going to buy the butter? That is what item set actually means is. Okay, so now I created another combination of two items, okay, A and D. Go to every transaction, find out A and D. And then what is my third combination? A, C, D. How frequent these three are happening together? A, C, D happening twice. So what you are doing, you're trying to create the combination of different items and then going through the entire data set, find out the support of that combination, and if that is satisfying, if the support of that combination is greater than the minimum support, you are marking that as, you know, um, valid combination, right? So to simplify this process, what I'm going to do is I'm going to create a lattice structure, okay, which would be easy, right? So lattice structure actually looks like this. So initially we have a null set, okay. uh, this is how the lattice structure would simplify the process of creating the combinations of items, okay. Just let's look at this. Now I have how many items that what are different items that I do have in this transactional database? I have A, B, C, D, right? I have four different items, right? Now, out of these four different items, I need to create the combinations of the items, different combinations that are possible with these items. So the best way is to create a lattice, okay? Look at this. Uh, how do I create the transactions out of this? As we know, if you are given with n number of items, the total number of item sets possible are 2 to the power of n, right? You know that, right? If you're given with 3 items, the total number of possible item sets that you're able to create is 8, right? Including the null set. That is what we have seen before. Where we have seen, here we have seen, right? If you're given with n items, the total number of possible item sets that you can create is 2 to the power of n. So with the 4 items, you will be able to create 16 item sets, right? So to find out 16 item sets in an easy way, this is one of the approaches, the creating a lattice. How does the lattice looks like? So we are creating with a null set and we're creating with one item sets altogether, A, B, C, D. Okay. These are the 4 different items that we do have. Now I'm going to combine A with B, AB, AB, AC, AD. Okay. So these are one item sets. These are two item sets. Okay. Why we are calling this as two item sets? As the cardinality of this set is 2, right? The number of items in this item set is 2. Any item set that falls in this particular line will have item set as 2. That is the reason we are calling this as two item set space. So we have AB, AC, AD. So those are the two possible combinations. And you don't need to combine B and A back again because it is already covered here, right? You doesn't need to combine A and C back again. This is covered. A and D doesn't need it because it is covered. So it is okay to just go forward. You don't really need to come back and combine with the done items. Now A is done. Going back to B now. Now I'm going to combine B with the items that are available forward to it. Okay. Now I'm going to combine B with C, B with D. Okay. So I don't, as I told you, once B is done, B is combined with C and D. So you don't need to come back because B and C covered here, B and D covered here. And then C and D, combining C with the forward one, which is D. Okay. I don't need to come back to D and C as D is, as it is covered here. So that is how we create two item sets. And the next step would be to create the three item sets. Three item sets means look at this A, B, C. Okay, A, B, A, C will become A, B, C. A, B, A, D will become A, B, D. Okay, that is done. A is done. Now B, C and B, D becomes B, C, D. Okay, now B is done. We have C. C cannot be combined with anything. If you look at this, BD is covered here, CD is covered here, AC is covered here, AD is covered here. So everything is covered. AC, AB is covered. The reverse is covered. So in Lattice, to simplify the problem, you can just go forward and combine with the forward items. You don't need to come back. Okay. Doing that way, now I'm combining these three item sets. So this is three item sets. And now you go to 4 item sets. Now you go to four item set, which is, what is that? A, B, C, D would be the one, because A, B, C, A, B, D combined would become A, B, C, D. So that is all we have. We don't have anything to combine with BCD in the forward direction. So the BCD is already covered here. So this is called as fourth item sets. Now, if you count the number of items, you have to get 2 to the power of 4, which is 16, right? Look at this. You have 4 here, which is 4 one item sets. You have 6 2 item sets, 3 1 item sets, 1 4 item set, and you have null set as 1. If you calculate this, 6 plus 10, 4, 14, 15, 16. So that is what 16 is. Now you have, this is how you create the combinations that are possible with the items that are given, okay, using this lattice structure. The other way to do it is, you know this binary form of representing, right? 0 0 0 0 0 0 0 1 0 0 1 0. Okay, so this is computationally simple when compared to that. Okay, combining the forward elements and just deriving the items out of it. Right now, going back to the problem. So the first step, as I told you, is to create the possible combinations, right? The second step of this would be to calculate the support of each item set. Okay, and what we do as the next step, we calculate the support of each item set and see if the support of that item set is greater than the minimum support or not. What is the minimum support given here? Which is 3. Now we have to go calculate the support of each item set and make sure if that is greater than 3 or not. If that is greater than 3, that item set is of our interest. Okay. Now go back there. What is the support of A? What is the support of A? This is the transactional database. This is the item set. One item set. What is the support of it? Hello. What is the support of A? You just have to go calculate the number of transactions in each A has happened, right? So A happened in first one, third transaction, and fifth transaction. So the support of A is 3. What is the support of AB? Support of AB is 2. It happened here in AB. It happened here in AB. So support of AB is 2. Okay. Now what is the support of B? Support of What is the support of B? In how many
Three.
transactions B has happened? 4, right? 1, 2, 3, 4. In how many
Four.
transactions D happened? 4. In how many transactions D happened? 5, right?
Fine.
And in how many transactions AC happened? 3. In how many transactions AB happened? To read this one and this one. Only 2 transactions. In how many transactions AD happened? AD, 3, right? So what is the support of PC? Support of PC is nothing but in number of transactions PC has happened. BC happened in 3 transactions. What is the support of BD? Support of BD. 4, right?
Four.
It happened in 4 transactions. Support of CD. 4. What is the support of ABC? 2. What is the support of ABD? 2. What is the support of BCD? 3. What is the support of ABCD? 2. Right? Now you calculated the support of each item set. Just also carefully observe the steps that we're doing. The first step that we have done is candidate generation or candidate enumeration. So we generated the candidates possible or the item sets possible from the items that are given to us. Like if you're given with 4 items, we just derived all the possible item sets from the four items given. So how many number of possible item sets from the given items? It is 2 to the power of n, which is equal to 2 to the power of 16. Right? So that is the first step that we have done. What is the second step that we have done? Second step that we have done is calculated the support of each of the item set. Calculating the support, what we have done, we have taken the item set and we have gone through every transaction in the database and calculated if that is present there or not, and summated. We have done the summation for all those transactions, or the cardinality, find out the cardinality of all those transaction sets in which A has occurred. So for B, again, we have gone through all the transactions. For C, we have gone through all the transactions. D, we have gone through all the transactions. AB, we have gone through all the transactions. AC, we have gone through all the transactions. So for every item set, we have gone through all the transactions. We have traversed all the transactional database and we calculated the support. Okay, so that is the second step that we have done. The major thing that you have to observe is for every item set, we have gone through all the transactional database. We iterated through the databases again and again, which is more complex computationally, right? It is literally very highly expensive in terms of computations, in terms of computational capacity, because we are traversing through the same set of database again and again for each of the item sets, right? The reason being, if right now you're just looking at 5 transactions, but in real world, how many transactions will happen in per day? It would be around billion transactions, more than billion transactions in on an Amazon website. So for calculating the frequent item sets, going through iterating through the database um, for such high amount of times is computationally impossible. Let's suppose if Amazon has 100 products, 2 to the power of 100, right? If he has 100 items in its store, the total number of combinations possible with 100 items is 2 to the power of 100. And if you're traversing through the database for every time for 2 to the power of 100 times, I mean, for 2 to the power of 100 items, it is computationally, let's suppose if you have 1 billion transactions, so iterating through the database, these for this amount of time is computationally very expensive, right? That is the reason it is called as naive approach, which is like a dummy approach. Just an initial understanding of this approach is that is how our thinking will be, right? Just find out possible combinations, go to every transactions and find out in how many transactions it happen and calculate that. If that is greater than min sub, that is a valid item set. That is how we actually do it. But just understand that it is computationally impossible, computationally very expensive. Now let's calculate the complexity. Complexity is nothing but the number of what is the computational efficiency or the computation cost of this particular approach. So 2 to the power of n is nothing but 2 to the power of n. If I generalize, n is the number of items. 1 billion is nothing but the number of transactions, right? If I say the number of transactions is m, that is called as m. Okay, so this is 2 to the power of n into m. That is the computational complexity of, or um, time complexity of this particular approach. Okay, complexities is determined by big O notation. Okay, what is this complexity? Complexity determines how good your approach is. That is what it determines. Okay, that is denoted by 0. When this is going huge, your approach is not good. If this is less and coming to a constant, that is a good approach. Okay, that your approach would be good. The number of iterations should be very less. When the iterations decreases, the computations will be decreased to a very less amount of time, right? If 1 billion is reduced drastically, so you're reducing, for each reduction in this 1 billion, you're reducing 2 to the power of 100 times of computational cost, right? That is what it actually means is, so reducing the time. So now what you want to reduce, your goal, this is a naive approach, right, that you have followed. Now you want to reduce this computational efficiency, right? Computational cost, iterating through the database every time for 202 to the power of n times, where n is the number of items, is computationally very cost. So that is why this is naive approach. But we just want to improve this approach, but you need to better this approach. That is what you're going to study in the next slides. Okay, but before going there, let's find out what are the frequent item sets from this approach that we have just done now. Okay, now look at the lattice that you have created now. In the lattice that you have created now, okay, what are the frequent item sets? So go to every transaction and find out what is the frequent item set in this case now. So 3, A is a frequent item set, right? Support of A is 3, which is greater than or equal to min sub, which is 3. So this is a valid item set. B is a valid item set. C is a valid item set, D is a valid item set, because for all of them, the support is greater than or equal to 3. Coming to AB, AB is not frequent item set because support is just 2. AC is a valid one, AD is a valid one, BC is valid, BD is valid, CD is valid, right? And now coming back to ABC, ABC is not valid because support is 2. ABD is not valid, support is 2. And BCD is valid, right? And ABCD is also not valid because its support is 2. Okay, so this is the frequent pattern item set that you're trying to solve. This is what you're trying to find out. Okay, from this you can recommend, if someone is buying he will also buy D. That you can say. If someone is buying A, he will also buy C. If someone is buying B, he will also buy C. Okay, if someone is buying BC, what he will also buy D is what you can say. If someone is buying only B, you can recommend C and D products as well. Okay, that is how you will design rules that you will come later, how to actually recommend the products based on the findings that you have done or the frequent item sets that you have found. That's a different story. We will come back to that later. But right now, what you have done, you have found out the frequent item sets, right? Using the naive approach. Naive approach means it's computationally very expensive. It is a dummy approach that you have done. What you have done, you have created all possible combinations from the items that are given, and for each item you have traversed to the entire transactional database, found out its support, and then calculated if that support is greater than the minimum support or not. If it is greater than minimum support, you added that to your frequent item sets. This is what you are trying to find out, right? At the end, this is what you're trying to find out. This is one of the approach which we call it as naive approach. Okay, now just think for 2 minutes. How do you want to better this approach? Is there any way that you can improve the efficiency of this particular method? That is what you just want to give it a try now. Okay, so just give it a try for the same, and I'll be here shortly. Okay, so you look at this stuff here. So if AB, just focus on this. So am I audible? Hello? Hello?
Yes, ma'am.
Okay. So just look at this space altogether. So at candidate enumeration or candidate generation, we can just improve this stuff, right? So just focus on this part. Just focus on this part. So once AB, okay, became infrequent, all its supersets became infrequent, right? It makes sense also. Just if AB cannot be frequent, how come ABC can be frequent? How come ABD can be frequent? Okay, so this way you can reduce the number of items, right? Item sets, right? Number of item sets. You reduce number of item sets. Okay, in just 16, if you eliminate this particular if you eliminate this particular row, you have reduced almost like 30%, right? Or 25% of this is reduced. Okay, so you saved some time on candidate enumeration. So technically what happens, it also reduces the number of times that we iterated through the databases, right? So the next approach is called as a priori algorithm. What that actually tries to do is um, you will prune the space. That means like you shouldn't look at those parts of search tree, yeah, that cannot be frequent. So once you know AB is not frequent, just stop going to the next steps. Generating the next item sets from that particular item set. So if you stop that, you will save some generating some infrequent item sets, even though that you are aware of. Okay. So if I know AB is infrequent, I'll stop generating the items coming out of AB. I'll just directly go to BC. Okay. So that is what I'll do, so that I'll save the iteration time related to these item sets, and also candidate generation time for those item sets. Okay, so that is what the next approach says. If X is frequent, then any subset of X must be frequent. Okay, if X is not frequent, then any superset cannot be frequent. It's a simple rule. If X is not frequent, if I call this as X, if this is not frequent, any of its supersets cannot be frequent, right? If this is frequent, we can say all its subsets are frequent. If AB is frequent, we can say A is frequent, B is frequent, right? If AB is not frequent, any of its supersets cannot be frequent. Okay, that is what it actually that it all comes down to. If AB is not frequent, any of its supersets cannot be frequent. If, let's say, if A itself is not frequent, any of this cannot be frequent. AB, AC, AD, all of this cannot be frequent. So you can just ignore all this tree, okay, and can directly go to B. So that is one of the ways to prune the space. So that approach is called as a priori approach or a priori algorithm. Okay, so this is what we have seen, right? Lattice structure. The set of item sets in a frequent pattern mining forms a lattice structure. Okay, all possible item sets in a frequent pattern mining, where the nodes represent, this is a node, represent the item sets, and edges connecting item sets based on their subset relationship. Edges is something which connects the item sets based on the relationship. This structure is often leveraged to improve the efficiency of the frequent pattern mining. Okay, mining algorithm. You have seen lattice structure. You also have seen how did we generated this. We calculated the support of everything, and once the support is less than 2, the next approach that we're going to do is we ignore all the item sets that are going to be derived from that item set. So all of this will be ignored. We directly go back to what is that? Uh, Directly go back to the next one, ACD. We will ignore all these item sets. Understood. So that is the next approach. So this is how the lattice structure looks like. We haven't generated the duplicates. Anyways, we will not generate the duplicates as we go forward. But here is where you will see all the possible combinations. So once we know A is not frequent, we ignore all the items that's generated out of AB. So these are all what are generated from the AB. Okay, and then you directly go to ACD, BCD, and all that stuff. Okay, that is our next approach, which we call as a priori. The levels, lattice organization is organization levels. We also know this is first item set because the cardinality of these item sets is 1. This is second item set, this is third item set, and this is fourth item set. You all know this. Nodes, each node in the lattice represent an item set. This is called as node. This is called as node, right? This is looking like a tree data structure. So everything that is related to tree would also valid here. This is just a tree. We arrange the lattice structure is nothing but just a tree structure and data structures. Okay, so every concept that applies for tree data set can also be applied here. Okay, and now you know this. So you know what are nodes. Nodes represents item set. Edges connecting two item sets where one item set is obtained by adding exactly one item to the other item set. So how we are forming AB for one item set, which is A, we are exactly adding one another item set. So you're getting AB. If you come back to ABC, for item set AB, you're just adding exactly one item set, which is C. So that is forming AC. So edge connecting two item sets where one item set is obtained by adding exactly one item to the other item set. So we are getting this item set ABC by adding exactly one item to the item AB. So that is what uh, item set actually means is. Understood? Now, this is what a lattice structure actually looks like. Okay, this is how lattice structure actually looks like. So we have levels, which is one item set, two item set, three item set, four item sets are called as levels. Nodes represent the item. Nodes basically represent the item sets, and edges represents the connection between the item sets. Okay, so ABC will become the superset for AB. A becomes the subset for AB. Okay, it's simple. So if AB is part of ABC, right? So A is called as the subset of AB, and A is called as the subset of AB. And ABC is called as superset of AB. So ABC is superset of AB, and AB is subset of ABC. Just remember the terms. ABC is superset of AB. Okay, ABC is superset of AB, and now AB is subset of ABC. AB is subset of ABC. Okay, AB is subset of ABC. All right, that is how you have to understand the relationship between the edges. Okay, anything which is part of the other item set would be the subset of it. Anything that is including other items apart from the items that we are looking forward is the superset of that particular item set. Okay, this is the lattice structure in frequent pattern mining. So now we are improving the approach. How we are improving the approach? So just read this, what it is saying. Prefix-based extension. We already doing a prefix-based extension, right? We already doing a prefix-based extension only. What we are doing, we are just adding, we are taking A, B, AC, AD. So based on the prefix we are adding, and then going to B, BC. We are not coming back, right? Only the based on the prefix we are adding. So AB is the prefix here. We are adding AC to it. For AC, we are adding, AC, AB, D. So we are adding prefix for this. For AB, D is added. So this becomes something like we are just adding one item for the previous item sets. So that is what prefix-based extension is. We are already doing that. But how we are actually improving the efficiency? We are improving the efficiency by ignoring the items where we have infrequent items, right? So a technique where item sets are extended by systematically adding items using prefixes to guide the generation of the item sets. So we are doing that. For every item, we are taking the prefix and we are adding the items to it. We are actually doing that. There is no problem with it. But instead of generating item sets randomly or naively, we extend an items. We are extending an existing prefix, a subset of items, by adding additional items. When we proceed with that approach, only when we go ahead with it, only when the prefix is frequent. So we are going to extend the prefix only when the prefix is frequent. We are not going to extend it if the prefix is not frequent. We are going to extend it only when the prefix is frequent. So that is what we are doing to improve the efficiency. Okay. It leverages the a priori property which states that if an item set is infrequent, then all its supersets must also be infrequent. This allows us to prune certain item sets early on without even calculating their support. So when we exclude those item sets, we are getting the benefit of not calculating the support of all those items, but also, uh, you're what you're doing, but also you are also saving some time of candidate generation also, right? You're not going forward, and also you're not enumerating the possible combinations out of that infrequent item set. So that is what improving the efficiency means. So the best example for this is, if you take the same example, how many items that we have excluded in this. So here we have 16 items, right? Technically, how many items that should come out? Initially, 16 items are there. We have to generate 16 items in naive way. In naive base, in naive approach, we have to generate 16 items, and we have to calculate support for all the 16 items. But When you exclude this tree, as you know, AB is infrequent. When you exclude these four items, how many you are generating now? You are just generating 12. Okay. And you're calculating support only for these two items. So now how much of time that you have saved? Let's suppose if you're for 16, if you're taking 1 hour of 60 minutes for 12 hours, for 12 cases, how much time would you take? It is 12 into 60 by 16, right? Which is somewhere around uh, how much that comes down to? How many minutes? That comes down to 45 minutes. So you're saving 15 minutes of time, right? So you look at that portion, 25% of the execution time is reduced by just pruning the space using a priori property. What a priori property says? A priori property says if the item set is infrequent, then all its supersets must be infrequent. So there is no use to generate them and calculating the support of them, just like what we have done in naive approach, right? You can discard all of them. So that is how you save some time. That is one of the best approaches. And naive approach is just the best approach in candidate generation. We cannot do much better than that when coming to candidate generation. Candidate generation is the first step, but we will try to look at even for 12 items out of 16, we pruned the item set space to 12 item sets, right? Now, even for these 12 items, you have to go through the entire transactional database, right? At least 12 times. So what I'm saying is, this is the best. What a priori is doing is the best. We cannot actually improve in this space. A priori is reducing 16 to 12 from this is naive and this is a priori approach. Okay. This is a priori approach. Okay. And these also have other names. Let me name them shortly, but there are also other names. Okay. So what you have to understand here is that 12, this is the best. Okay, you cannot do much better than this, reducing from 16 to 12. Technically, ignoring the infrequent supersets, if an item set is infrequent, that is the best thing that you can do at candidate generation. Now, if you want to improve this process much better, you have to do something in this transactional database, right? So if you get 12, you're traversing through the entire transactional database 12 times. Okay. You're traversing through the entire database 12 times. So if you can reduce these transactions, okay, you can improve the process. You can get this done in less amount of time, or finding the frequent items in less amount of time. So let's focus on how can we reduce that. But before going to that step, just understand the a priori algorithm. What a priori algorithm is doing? A priori algorithm is also called as breadth first search or level wise. Level wise. Why it is called breadth first? Breadth first search. You know what is breadth first search is? Breadth first search means you're going from left to right, level wise you're going. After completing this level, then only you will go to the next level. After completing this level, you will go to the you then only will go to the next level. Okay. You will not come to the next level until unless you complete the previous level. That is called as breadth first or level wise. Okay. There is another approach called as depth first. Okay, this is breadth first, means you will complete all these things, all these items in the level at one go. Whereas breadth first means you will complete all this level at one go and then you will go to the next level. Okay. Breadth first means going down, complete that entire level and coming back to the next level. Okay. Whereas breadth first means complete all the items in that level and then only come to the next level. Okay. This is breadth first search because how we are actually generating the item sets. You're generating this way, right? Candidate generation is happening this way. How it is happening? You're creating null and then A, B, C, D, E, and then generating A, B, A, C, A, D, A, E, B, C, B, D. You're generating this way. You're generating this way, you're not generating A, B, C after without generating A, C, right? You're not going down, you're generating all the items of this one. Once A is generated, BC is also generated, B is also generated, C is also generated. You're not going down from A to AB, all the levels, and then you're not going this way. You're not going this way. You're going this way, right? So this way, going this way is called as level wise or breadth first search. Going this way. Where is this BC? Going this way is depth first search. Going down to the end of the tree and coming back to the next level is depth first. Going level by level is breadth first search. So a priori algorithm is breadth first search. What is the main intention of a priori algorithm is, if an item set is infrequent, ignore all the supersets of that item set. So we ignored all these item sets from this. So now by doing this, how many items that we are reducing? Let's calculate this. Here is 5. Here is 3, 6, 9, 10. Here is, you have 2 to the power of 5 technically. What is the 2 to the power of 5? 4, 8, 16, 32, right? 4, 8, 16, 32. So total you have 32 items in this lattice. How many are you excluding? 3, 6, 7, 8. Out of 32, you are excluding 8. So that is becoming, how much is that? 24, right? So out of 32, you are pruning 8. That becomes 24. Okay. If the using just one property, which is if an item set is not frequent, none of its supersets can be frequent. Okay. So what is this doing? This is just, initially we understood that complexity of the naive approach is 2 to the power of n into m, right? 2 to the power of n into m. What is the complexity of this a priori approach? It is the same. I would say 2 to the power of t into k, whereas t is less than n, t is less than n, k is less than m, right? So it is reducing some sort of enumerations, and when enumerations are decreased, support calculations will be decreased, so that number of transactions to the database will also be decreased. Okay, this is what a priori algorithm is. This is the second approach that we were talking about. And now we will go to the third approach. What we have just discussed. What a priori is doing with the candidate generation is the best. We cannot improve that part. The only part that we can improve is the um, traversing through the database part, right? Traversing through the transactional database part is what we can improve, right? So let's go have a look at that now. Uh, so how can we do that is what is our interest right now. Let's me go back to the next slide and talk about that. I think this is what I sent it. It's blank for a priori. I hope you understood what is a priori is. So I think it is clear for you. You just prune the space compared to the naive approach. Now, if you just compare the differences between naive approach and a priori approach, candidate generation. So you generate 2 to the power of n candidates. -1 is just to ignore that null set, or null set which is 5. You just ignore that. That's the reason it is mentioned as 2 to the power of n minus 1. Okay. And then what about a priori? A priori generates candidates level by level. That is why it is called as breadth first search. So because level by level based on frequent items, if something is not frequent, it will just ignore it, right? That is something that you have to actually look at now. All right. So and now uh, now pruning. There is no pruning in a naive approach. It checks all possible item sets. It prunes the space, saving computational time. Whose subsets are not frequent, that efficiency, computational expensive. It is exhaustive search for every item set. more efficient due to pruning and reduced candidate generation. It is better compared to naive approach. What is the time complexity? 2 to the power of n into t. What is the time complexity of this? It is similar, but it is lower than 2 to the power of n into t, because n is less than here, n is in naive a priori approach is less than n, t is less than this. It is much less than this, but in the worst case, if you don't have, if everything is frequent, if all the item sets that is generated, or of all the candidates generated are frequent, then that approach, I mean, a priori algorithms time complexity would be same as this one. Space complexity higher because it generates all and stores all the possible item sets. Only frequent item sets are stored. Instead of storing all the 16, we are just storing 12. So space complexity, the amount of space that is required to execute this algorithm, is lower in a priori algorithm. If it is naive approach, even though they are not frequent, we are storing 16 item sets, right? We are storing 16 item sets. So the rest of the 4 item sets also need some space in the memory to be stored. So we ignore them in the a priori algorithm. So space complexity is little much better in a priori algorithm. So these are the comparisons, and coming to computational efficiency and space efficiency. Now, as we have learned two methods, it's time to learn about you know association rule. What is association rule is? I Association rule is nothing but it's a rule that implies a relationship between the items in a data set. Okay, it is something that looks like this B. So to give a best example of this, let's suppose if someone is buying a book and a pencil, these are items bought. Okay, items bought implies, here I'll write it as eraser. This is B, this is A, and this is the relation. So if a customer bought book and pencil, there are high chances that he will also buy eraser. Okay, customers items also bought. Okay, so that is called as association rule. If someone is buying books and pencil, he will also buy eraser, or the probability of that particular customer buying eraser is also high. Or the basket analysis, if the basket contains book and pencil, there is high probability that basket will also contain eraser. Okay, that is what association rule is. That is why we are doing all that stuff, right? We are trying to derive all the possible combinations of item sets, and from those item sets we have to derive the association rule, so that based on the association rule, we will actually recommend the products to the customers, right? So that is what association rule basically means is. Association rule is a rule that implies certain relationship between the items in a data set. It is of form A and B, where A is the antecedent and B is the consequent. Antecedent means the set of items on the left hand side of the rule, and consequent means the set of items on the right hand right rule. Antecedent means if this happened, what is the consequent? This might also happen. Okay, so if you're given an association rule, the right side is called as antecedent and the rest side is called as consequent. Right side denotes, I mean, the left side denotes items bought, and the right side denotes the probability of this item is also bought. Okay, that is what the recommended product also can be said. The B is also called as the recommended product. Association rules are commonly used in market basket analysis to identify the relation between products that are frequently purchased together. Okay, so this is a rule that specifies the products that are frequently bought together. Two important metrics for association rules are, so if this association rule is valid or not, is something has to be found out, right? So you are saying book and pencil, when a customer is buying book and pencil, he can also buy eraser, is what you're saying. On what metrics you are saying that? Is there any number that specifies this confidence, right? So that has to be like um, you know calculated if this is valid or not. So for that, you have two things. One is support. You already know what a support is, right? Support is nothing but a number of transactions that particular item set has happened. You know how to calculate the support as well. And confidence. Confidence is something which specifies how confident you are with that association rule. Okay, how often that rule holds true is what the confidence is. Given that A occurs, how often does B also occur in the transactional base? Transactional database is what, you know, confidence calculates. Confidence actually calculates how often the items in the RHS appear in transactions that contains items in the LHS. It shows the strength of the rule. So this is the rule that you have derived. Calculating the confidence will specify the strength of that rule. You can also put a threshold on this confidence. If this threshold is greater than 0.8, then only consider that rule. You also have put a threshold on the minimum support. In similar way, you also put a threshold on the confidence of the association rule that is derived from the frequent item sets that you have got from the a priori algorithm or the naive approach. So for that, you have to calculate support and also the confidence. Confidence specifies, what does that specifies? It specifies how often B also occur if A occurred, right? If book and pencil occurred, how often that eraser will also occur is what confidence will calculate. What is the formula for that? Formula for that is nothing but support of LHS union RHS by support of LHS. Okay. Um, let's suppose if you're calculating for A to B, okay, if you're trying to calculate the confidence for the association rule A to B, okay, so now we are trying to calculate the support for the association rule A to B. We are trying to calculate the confidence. What is the formula for this? Formula for this is support of A union B becomes AB. Just when both the items occurring together, A and B are independent, right? They are different items and they are independent. Okay. So this is what you have to find out. Okay. A to B is there, uh, right? A to B. Now we are trying to calculate the confidence of this A to B. That means you have to calculate the support of AB. In what all transactions AB occurred together by support of A, which is in what all transactions A has occurred. So confidence of the rule A to B is support of AB by support of A, which is 4 by 5, which is 0.80. Right? So you will have, this means that if an item A is present on a transaction, then there is 80% chance that item B also will be present. That is what it actually calculates. Got it? So that is what confidence actually measures. But there is an hiccup with confidence. Okay. What is the hiccup with confidence is the reason is before going there, just understand what lift is. Lift measures the strength of the association by compare the observed support of A and B with the expected supports of A and B if A and B were independent. So there are high chances that B can also occur independently, right? It doesn't need to necessarily have a relation with A. Being both of them are independent, they also can occur independently. Okay. If you look at the denominator of this, you are not taking B part into it. Okay. You're taking union of it. You're taking A only. Okay. Which is on the left side antecedent. If this happened, probability of B happening is what you're calculating, or what are the chances of B happening is calculated, but you're not taking the effect of B happening independently. Okay, that is what the lift is being taken. Okay, B can also happen independently in the basket, right? If book and pencil is happening, B can also happen all the times. Okay, there might not be any association between the left hand side and right hand side. Being both of them independent, they can also if eraser happen frequently in all the times, you cannot actually, this confidence will fail to actually take that independence into consideration, as we are not dividing that in the denominator. Whereas what lift will do is it takes both A and B independent actions as well. As it takes both A and B, this would be the right measure of the strength. Measure the strength of the association by comparing the observed support of A and B with the expected supports if A and B are independent. If lift is equal to 1, if the value of lift is coming as 1, A are independent of each other. This is what confidence is not given. Whether they are independent of each other and they are occurring together or not is what it is not given. What it is just giving, it is just giving what are the chances of B occurring if A has happened. And now you cannot associate them, right? If both are independent, if both are going to the basket independently, you cannot associate them. They are independent and they are happening in most of the baskets independently. There couldn't be any relation between them. So that is what lift also says. If both are independent, lift will be equal to 1. If both are correlated, positively correlated, if one is happening, if the other one is also happening, that is 1. That lift is greater than 1. Negatively correlated means if one is happening, the other one will not happen. That is negatively correlated. So that is what lift values actually means is that is the difference between confidence and lift. Lift will also consider the independence of both the items happening together. Okay. So that is something which you have to find out. And going back to the next slide. So here is what why this is the explanation of this. Why do we need lift when we have confidence? We have confidence, which is also giving the strength of P, P occurring if A has occurred. But why do we need lift? So this actually tells us that. Okay. Now let's just try to understand this part. Confidence only measures how often B occurs given A has occurred, but it doesn't tell us whether this association is actually meaningful or just due to chance. Okay, it just happening if B is frequent is if they are independent, if A and B are happening in most of the baskets independently, that is not what confidence will give us. For example, if B happens to occur frequently on its own, even without A, then the high confidence could be misleading. Okay. Um, High confidence could be misleading because let's suppose look at this example. If B happening more frequently, right, then this value will increase, right? 0.5 by 0.67 says 0.75, which what is this interpretation means basically is what is this interpretation giving us? Giving that bread was brought, butter was brought 75% of the times. Okay, as bread has occurred most of the times, you got this value 0.75. Okay. Uh, so this is coming to be 75% of the time. Bread is bought, butter is also brought is coming to be 75% of the times. But if you calculate the lift, what you have got? You have got 1.12. Okay, 1 is independent. The additional percentage 0.12 is the probability of buying butter if bread is brought. A lift of 1.12 means that buying bread increases the likelihood of buying butter by 12% more than if they were independent. A lift of greater than 1 indicates positive association. So the lift is giving 20%, 12%, whereas the confidence is given 75%, which is misleading. As count of the bread would is more or is occurred independently more number of times or frequently, it is coming to be 75%, whereas this is coming to be 1.12%. Okay. Confidence says 75% of the time when bread is brought, butter is also brought, but lift tells us that is only 12% increase over random chance. If butter was purchased 60% of the time regardless, then the high confidence value might just reflect the fact that butter is frequently purchased, not necessarily a strong link with the bread. 67% of the time regardless of the butter, it is brought independently. So that necessarily needs to be with the bread. So when you divide that with bread and butter, they should happen independently. I mean, they should happen together. In the numerator and denominator also, you're keeping that together. So lift gives a clear understanding of whether buying bread genuinely increases the likelihood of buying butter, of if it is just due to butter being generally popular. Okay. So when you want to find out the right association, you always has to calculate the lift, because butter confidence can mislead if the denominator, um, I mean, if the denominator, which is antecedent, is happening independently for lot number of times. Okay, that leads to misleading value. When you calculate, for in this example, when you calculated the confidence, you got 0.75, which is 75%, which is really misleading. Okay, now if you understand that you got 0.75 here, right, and 1.12 here, so it's only increased 12% of the probability. Okay. So if bread is happening, both of them occurred in 0.5 percentage only, but bread happened independently in 67 percentage of the transactions. Okay. So they both together happened in only 50 percentage, but independently happened more number of times. So that actually leads to, that would be misleading, that you got 75 percentage. Here you are just considering only the transactions where bread happened independently, not the transactions where bread and butter happened independently. You have to take both the transactions to find out the right correlation between the both the items, or the dependency of one item on the other. So that is why you will also calculate the lift along with the confidence. So that's the reason you need to go to the lift most of the times to find out the actual association between both of them. Now, how to find out the association rule is what you have to find out. So you are saying association rules, right? How do we actually derive those association rules is what you will study right now. So I'll give you an example. Let's suppose I was given with this one. Let's suppose I got ABC as my frequent item set. If I got ABC as my frequent item set, how to write the association rules for from that frequent item set? Okay, let's understand that. From my a priori algorithm, or what is that? Naive approach. What I have got is the item sets, right? I think all got arranged. We got the item sets. Let's suppose if I got ABC as my frequent item set. If I got ABC as my frequent item set, which is the output of the a priori or the naive approach, how to derive association rules for this? So this is whole item set space for this particular item set, and I'll take one out of it. I'll take S, which is the subset of I. I'll take subset of I and I'll map S with I. So the association rule actually looks like this: S is tends to I minus S. This is antecedent and this is descendant. Okay, I minus S is descendant. Got it. So now what I'll do here is that I'll add now to for me to write the you know for me to write the association rules. This is how I'll write the association rules. Let me go back to that blank slide to go look at that. So now I'm trying to write the association rules. Okay. So how do I do the association rules? This is how, let's suppose I got this ABC as my association rule after applying the priori algorithm or whatever it is. Now, to derive the association rule, what I'm saying, the association rule actually looks like I minus S. Okay, where I is the whole item set, S is the subset of the item set, S is subset of item set. Now, to derive the association rules out of this, I'll take A as my S. Okay, I'll take A as my S. So thus this becomes BC. A to BC. I minus S means out of this I, ABC, you have to subtract S, which is A. Now the second one would be B, AC, C, AB. Now take two combinations, AB, C, BC, A, AC, B. Okay, so these are the possible association rules that we can derive. Okay, these are the possible association rules that you can derive. That means if product A is brought what is the probability of, I mean, there are high chances that products B and C could also be brought. Okay, this is association rule 1. If A is in the basket, there is high probability that B and C will also be in the basket. Item brought, items will also be brought. Okay, now you have to calculate the confidence of this association rule. If you have the threshold of 50% of this confidence, now you have to calculate the confidence of this association rule. Confidence of this association rule is nothing but support of ABC by support of A, right? That is what actually confidence calculation actually means is. And what is lift? Lift is nothing but S of ABC by S of A into S of BC, right? You take both left and right, whereas in confidence you take only the left. You can look at this. On confidence is just the LHS. Lift is nothing but both LHS are HS. On the top you will get the union of both of them. Anyways, that would be ABC. So for this association rule to be valid, you have to calculate the confidence, and this confidence value has to be greater than the threshold value that you have set. If you set the confidence as 50%, this when this confidence is greater than this 50%, then only this association rule will be valid. How we are deriving these association rules? You are deriving these association rules from the item set that we have got. How we derive this item set, frequent item set, by following the naive approach or the a priori approach. We created all possible item sets and then calculated the support of each item set, and then we validated if the support of that item set is greater than or equal to the minimum support. Once that is satisfied, that becomes a frequent item set. From the frequent item set, you are deriving the association rules. Association rules are derived like this: S subset of I tends to I minus S. So these are the association rules. For this association rule to be valid, it has to get the confidence value greater than the threshold confidence value, which is 50%. It's user defined. You can set it as 60, 70, 80%. So let's suppose if the confidence of this is 50, if the confidence of this is 10, if the confidence of this is 20, this is 90, and this is 80, this is 70. If you have set the threshold as 80%, then the valid association rules would be only this. Then you will get these association rules, right? Then if there is a in the basket, if you have say A and B, you will also recommend C. When this association rule is not satisfied, when the customer bought A, you will not actually recommend B and C. Okay, as that association rule is not valid. Okay, that's how you build the association rules, and then the products will be suggested to the customers. Got it? So this is all about constructing association rules. You will form the association rules, and that is how you calculate the confidence of an association rule. Association rule. Okay, that is what about association rule. And now coming to ECLAT algorithm. Okay, this is what I'm talking about. So as I told you earlier, a priori algorithm is doing its best in generating the candidates. Candidates are nothing but all the possible item sets, right? All the possible item sets here are the candidate generations. A priori algorithm is doing its best as it is pruning the space by ignoring the supersets of an item set where the frequency is less than or the support is less than the minimum support, right? That's how it's pruning the space. It's pruning the space, and the transactions and the candidate generations also getting down. For the example that we have seen, it has got down by around 25%. And now where we can do better, we can just do better at the transaction end, right? In transaction generation, we just need to do, we would like to try our best to reduce the amount of time that the iterations are taking, or what it is called as traversing through the database. That is what it needs to be improved now. So we will work on that now, and we will see the approach that actually improves that particular part. All right. Now look at this carefully, how we are actually doing this. So the first step in, you know, um, ECLAT algorithm. This approach is called as ECLAT algorithm. You will understand why this is called as ECLAT algorithm shortly. ECLAT full form is equivalence class transformation algorithm or vertical TID set approach. Okay. Um, just give me 1 second. There's a message. Okay. So what we do in this ECLAT algorithm is that it is called as vertical TID set approach. Okay. Carefully observe what we do as the first step is we generate this transactional database into a vertical format. This is the transactional database that is given to us, and we convert this to, you know, uh, the vertical format. Okay, I just have to edit this. I think this is not right, but let me show you how we can do it. So we create an vertical. We convert the transactional database to vertical format. What that actually means is that, okay, so look at this. So this is what I will actually do. So I'll convert this to vertical format. That actually means is in transaction one, you have ABDE. In transaction two, you have ABDE, right? I'll change this to this way. So what are all the items that I do have? I have 5 items, which is A, B, C, D, E. So these are the items that I do have. Now, when I say converting the transactional database to vertical format means this would be the set of all the transactions in which A is present. The item A is present. That means it is present in transaction 1, 2, 3, 4, and 5. Okay. So that is what I will do. I'll go to each item and find out in which all transactions that particular item is present, and I'll form a set of that is called as vertical representation of it. And just I you will shortly see how does this actually reduce the time that we are talking about in iterating through the databases. If I go back to B, in which all transactions it is present in all 6, right? 1, 2, 3, 4, 5, 6. It is present in 1, 2, 3, 4, 5, and 6. What about C? C is present in 4, 5, 6, right? C is present in 4, 5, and 6, right? Look at this transaction database. C is present in 4, 5, and 6. In which D is present? D is present in 1, 2, 3, 1, 2, 3, 5, and 6. In which E is present? E is present in 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now we converted, we are done with our first step. The first step is to convert the transactional database to vertical format. Vertical format means it is here the transaction ID to the items mapping, right? Item set mapping here. Item to the transaction set mapping, TID set. This is basically the TID set, right? This is what you will say. Now using this vertical format, how do I do right now is that this is a breadth first strategy. Okay, ECLAT algorithm is breadth first strategy, whereas a priori is this is ECLAT is depth first strategy, and that is breadth first strategy. When I say depth first strategy, what does it actually means is now the next step is to generate the lattice of these combinations, right? When I say lattice, how do I actually generate that? This is how it looks like. So now I got this transaction set. Now what I'm going to do is I'll create an transaction set now. So this A becomes A, B, C, D, and E. Okay. Now A is present in 1, 2, 3, 4, 5, 6. B is present in 1, 2, 3, 4, 5, 6. You have this vertical format, right? Now what I'll do is I'll go back to AB. I'll form this, and now I'll go to AC. Okay, I'll go to AD. We are going through depth first now. Okay, we are not doing breadth first. Breadth first means going through all the entire row from start to end, but we are doing depth first. So I'll just stop generating until A, all the combinations of A. From here, I have gone to E. Now what I have done is, look at this. So when I say AB, I'm not going to traverse through all the database again. Okay, understood? So how do I capture this? I have gone to first transaction ID and I got A. So I have placed it in A. B, have B. So I placed one in B. C, I don't have. So I haven't placed one. D, I don't have. E, I don't have. So one time I have gone here. Second time, I'll go to the next transaction, update all these records. Third time, I'll go to third transaction, update everything. Fourth, I'll update everything. Fifth. So I have traversed only once through the entire database and got this data, captured all this data. Now from this data, from now onwards, I'll never go to this transactional database again. I'll only use this data set. Okay. I'll only use this vertical format to calculate anything, to calculate support or whatever it is. Now, when I want to calculate the support of AB, what I'll do is I'll take the intersection of these two. What is the intersection of these two items? It is 1, 2, 3, 4, 5, right? It is 1, 2, 3, 4, 5. Okay. Now just remember, just take the example. This is just an example. You have 5 items and 6 transactions. But in real world, there would be items is nothing but the products, right? You have 100 items, but the transactions would be millions or billions, right? So you're pruning, I mean, you're converting a million rows to just 100 rows, which is like 100 products. And you will get all the transaction IDs here. So that simplifies, that improves the computational efficiency. Now from here onwards, you're just going through all these 5 records and you're just finding the transaction, I mean, intersections. After now, you will find AC. What AC is? The intersection of these two, right? 1, 2, 3, 4, 5, 4, 5, 6. Intersection is 4, 5. What is intersection between A and D? It is 1, 2, 3, 5. Right? It is 1, 2, 3, 5. What is intersection of A and E? What is intersection of A and E? 1, 2, 3, 4, 5. Got it? Now you got this. Now you will also store these transactions. Okay, 1, 2, 3, 4, 5, 4, 5. These are also been stored. Now when you go to the next stage, you will not go to BC again and saying because this is depth first. So you will complete one part now and then only you will go to the next one. Now here, what are the possible things? ABC, ABD, ABE, which is the combination of AB and AC is ABC, AB and AD is ABD, AB and AE is ABE. And now here, AC and AD is ACD. Okay, AC and AD is ACD. AC and AE is ACE. Okay, and AD and AE is ADE. Okay, you have formed everything that is possible in this layer. Now to find out ABC, you just have to find out the intersection between these two, 1, 2, 3, 4, 5 and 4, 5. So this is 4, 5. Okay, if you are given with minimum support as 3, what you will do? This is not frequent, right? So you will just ignore this. You will not extend this anymore further. What is ABD? What is intersection between AB and AD? 1, 2, 3, 5. What is the intersection between AB and E? AB and AE, which is 1, 2, 3, 4, 5. What about ACD? ACD is, oh, this is also infrequent, right? So you doesn't actually need to bother about ACD and ACE, as AC is not frequent. ACD and AC will also be infrequent. What about ADE? ADE is 1, 2, 3, 5. Got it? So when you convert this database into a vertical format, the finding the supports is becoming easy. So earlier, what you have done for every ABD, you used to traverse through all the million records to find out this, right? But now what you have just done now, you just have found out the integration or intersection of these two sets, which you have already calculated before. So this is how ECLAT algorithm actually reduced the computational cost of traversing through the entire transactional database, right? So this is what ECLAT algorithm. So once this row is completed, once everything related to, let me just extend this further for your understanding. So this is not frequent, this is not frequent, this is not frequent. So now we got ABD, ABE, ADE is also there. Now, um, what is this? This becomes ABDE, right? The next step would be ABDE. Maybe I would have taken a good slide, but let me just do that. Let me take this slide folder to, let me complete, retake a new slide so it would be easy. Now we converted the transactional database to this, right? Now this is our, what do we call it as, the vertical format we have now. Okay, this is the vertical format that we do have. Now we are trying to generate the, um, lattice from this and eliminate everything that. Okay, so now let me draw the lattice again to better explain this with the entire with one complete example of how ECLAT algorithm actually works now. So now let's look at this. Okay, let me draw the lattice structure for all these items. So how does the lattice structure looks like for this is, okay, so look at this. Options and colors. This. Now I'm drawing the lattice for this. Just carefully observe. So we have pi and we have A, B, C, D, and E. Okay. Now what is A? 1, 2, 3, 4, 5. Right? 1, 2, 3, 4, 5 is A. B is 1, 2, 3, 4, 5, 6. C is 4, 5, 6. D is 1, 2, 3, 5, 6. And E is 1, 2, 3, 4, 5. Right? Now, what I'm trying to send it, support, min support is given as 3. Okay. Let's take the min support as 3. Right. So the support of everything is greater than 3 because support of this is 5, support of this is 6, support of this is 3, this is 5, and this is 5. So everything satisfied the minimum support. Now we go extend AB, AC, AD, AE. Okay, so as we are going for the depth first search, we will only complete A for now. We will not go to B as ECLAT is depth first strategy. Now, when you want to compute AB, what is the intersection between A and B? It is 1, 2, 3, 4, 5 is the intersection of A and B. What is the intersection of A and C? It is 4, 5, right? 4, 5. What is intersection of A and D? 1, 2, 3, 4, 5, 1, 2, 3, 5, 6. Intersection is nothing but A is 1, 2, 3, 4, 5, right? And D is 1, 2, 3, 5, 6. What is common in both of this? It is 1, 2, 3, 5, 1, 2, 3, 5. That is common in both of them. That is what intersection actually means is 1, 2, 3, 5 is ADE, AD. And what about AE? It is 1, 2, 3, 4, 5. Now look at the support of this. Look at the support of AC. The support of this is 5, right? The support of this is 5. The support of this is 2. Support of this is 4. And support of this is 5. Now you know AC is infrequent, right? What you will do, you will just ignore that AC. So now AC is infrequent, so you will ignore that. You will not continue extending that further, right? So now you will extend from AB. So AB combined with AD becomes ABD, right? So AB combined with AE becomes ABE. That's all. Now AD combined with AE becomes ADE. Okay, so these are the combinations that you will get. Now what is AB, AD? What is intersection? AB and ABD formed from AB and AD, right? So what is intersection between both of them? It is 1, 2, 3, 5. And what about ABE? AB and AE is ABE. So that becomes 1, 2, 3, 4, 5. And what about ADE? It is 1, 2, 3, 5. So support of everything is greater than 4. Support of this is 4. This is 5. This is 4. Now we extend further. That becomes ABD and ABE becomes ABDE, right? ABDE. ABD and ABE becomes ABDE. So AD is also part of ABD, ADE, right? So now, what is intersection of ABD and ABE? Which is 1, 2, 3, 5, right? So this both of this formed ABDE. So ABDE is also part of this. Okay. So there is no further extension. ADE don't have anything to join. So ABD and ABE becomes ABDE, and so ABD and ABE forms AB. ABD and ADE also forms ABDE, right? So there is nothing beyond this. So AB and ADE forms ABDE, right? This forms ABDE. So AB and ADE also forms ABDE. So everything is covered here. So there is no extension further. Okay. Uh, Look at this. ABD and ABD and ABE forms ABDE. Okay. That's all. So ABD when combined with ADE will also form ABDE. ABE and ADE also forms ABDE. So everything constitutes to 1, 2, 3, 4. Support of this is also equal to 4, right? Support of this will also be equal to 4. Support of this will also become 4. Now, what are the rules that we derived from this? Association rules that came up from this. But before writing the association rules, now we go to second lattice. Okay. Now you can remove all this data from the, now as this is done, you can remove all this data, right? You don't need this data in the database anymore. You don't need the number of the transactions of A or AB or AC. This is already done. We got the transaction IDs as well. So you can remove all this data from your database. Now you can continue from BC. The next would be BC, BD, BE, right? What is the intersection of BC and BD? It is 4, 5, 6. BC intersection is 4, 5, 6. What is intersection between B and D? 1, 2, 3, 5, 6. What is intersection of B and E? B and E, it is 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. Now everything, support of everything is greater than 3. This is 3, this is 5, this is 5. So we extend BCD. So we extend BCE, and this becomes BDE. Okay, what about BCD? What is intersection? Intersection is 5, 6, right? What is BCE? What is intersection between these two? It is 4, 5. What is intersection of BCE, BD and BE? 1, 2, 3, 5, 6, 1, 2, 3, 4, 5. It becomes 1, 2, 3, 5. So this become these two. Support of these two is, what is the support of these two? Support of both of them is 2. Support of this is 2. Support of this is 2. So we will ignore both of them. So this is the end. We don't have anything to extend here. And once this is completed, we go back to the next one, which is CD, CDCE. Okay. So that is how you keep on going in the, from the left side. Once the depth is completed, you will extend on the right side. So that is why this is called as depth first approach. Now, when you got all the frequent item sets, what are the frequent item sets here? Frequent item sets are these, right? Frequent item sets are AB is a frequent item set, AD is a frequent item set, AE is frequent item set, ABD, AB, AD, ABD. Okay. Now, if you want to write the association rules for ABD, how would you write that? If you want to write the association rules for ABD, this is how you write. So now you want to find out the association rules for ABD. How to write association rules for ABD? There becomes S tends to I minus S, A, B to AD, and D to AB, AB to D, and all that stuff. Now, if you want to calculate the confidence of this, how do you calculate the confidence? Confidence would be nothing but support of ABD by support of AB. What is the support of ABD? It's nothing but 4, right? The cardinality or the length of this ABD by what is the AB? 5. 4 by 5 is nothing but 20 percentage, right? 80 percentage. Sorry. So 80 percentage. So the confidence is if I set the threshold as 60 percentage of confidence, this is more than, so this is a valid association rule. Now if you calculate for D by AB, what is the D? Support of D is 4 and support of AB is 4. 100 percentage of confidence for this. Okay. That's how you calculate the confidence of every association rule, and you recommend or you use those association rules to recommend the products. Okay, that is the final thing that you will do. So where did we improve the performance here? We improved the performance here, right? At the number of transactions we have not done these many number of transactions, right? We haven't traversed through the database million times, right? For if you have million records for 100 products, we have not traversed it through 100 into 1 million times. We have traversed only for 1 million time, and then how we are just traversing through these 6 records, right? Number of products records, number of products, right? Right. So the original would be 2 to the power of 100 into 10. So for every transaction, for every item set, so total number of item sets for 100 products will be 2 to the power of 100 into 1 million times we have traversed. But now we have just traversed only 1 million times to actually, get this vertical format. And once we got this vertical format, what we are just trying to do, we are just reducing the number of times we traverse through everything. So once we got these things, we are trying to find out the transaction intersections. So only the intersection efficiency, only these two records intersection, these two records intersection. So it drastically reduced it, right? The number of times that we reduce has become down to 1 million into somewhere around close to number of record times. So 2 to the power of 100 into 1 million is reduced drastically down to 1 million times. Uh, that is how the efficiency of this is drastically reduced for the ECLAT algorithm. So now once this is constructed, we are not going through the transactional database anytime. For getting AB, you're just trying to go through these two records, get the intersection of it, and do that. For AC, go to these two records and get that. Right. Once you got that, you're not even going there. You're using this data to calculate the next steps. All right. So this is how equivalence class transformation algorithm works. That is why it is called as depth first search. Depth first search, basically what it will do, you can save the memory once the particular tree is done. Once a particular tree node of a tree is done, you're just getting rid of that. So once this is done, you're no more storing the data of this. You can squash this data and go to the next tip of it. Okay. So this is more concentrated towards, you know, reducing the time that is required to calculate. At the database traversing or transactional database traversing. So this is all about ECLAT algorithm. Okay. Now we have seen naive approach. We have seen um, a priori algorithm. We also have seen ECLAT algorithm. And we also have seen what are association rules, what is confidence, and what is lift, why we need lift when we have confidence, which association rules has to be picked, and how to construct an association rule from a frequent item set. Okay, this is all what we have learned along with the key terminologies in the previous slides that we have seen, which is transactional ID set, transactional space, item set space, item sets, uh, TID set, and all that stuff. You also have seen support, item set mining problem, and all that, all those things. The next one is projection approach. Okay, what we do in projection approach and how does this work is something that you will learn now. It's a different way of getting the same thing. Okay, it's a different way of I mean achieving the same thing. How do we do in this is it's simple like this. Um, what we do in this thing is the first step for this is count the frequency of each item. Count the frequency of each item is nothing but what are the items that we do have. You have again 5 items, right? You have A, B, C, D, E. So these are the items that we do have. Count the support of each item. What is the support of A? Support of A is 5, right? Support of A is 5. Support of A is 5. What is the support of B? Support of B is 6. What is the support of C? It is there in 3 transactions. Support of C is 3. 1, 2, 3. What about D? D 1, 2, 3, 4, and 5. Support of D is 5. Support of E is also 5. So this is the first step. Calculate the support of each item in the transactional database. Once this is found, the second step is to create second step is to create frequent items. Okay, so second step is to find out the frequent items. So everything is frequent here, right? Every A is, let's suppose min sub is taken as 3. Min sub is taken as 3. Okay, if min sub is taken as 3, what you just have to do right now is, you know, calculate, I mean, identify the frequent items. In this, everything is frequent. 5 is frequent, A is frequent, B is frequent, C is frequent, because 3 is greater than or equal to 3, D is frequent, E is frequent. If something is infrequent, we just ignore that. Let's suppose if C is not frequent, we will just ignore that. So we will take only A, B, D, and E. If C is infrequent, if C, as here C is also frequent, we take all the items. Now, once we identified all the frequent items, we construct conditional pattern base. Okay, just look at how do we actually create this conditional pattern basis. Okay, now let's all the items that are now let's identify all the items now. So now we have 5 items here, right? So we everything is frequent, so we write A, B, C, D, and E here. Okay, now we have to construct the conditional pattern basis for these items. How do we actually create those conditional pattern bases is something that you're going to see now. Okay, it's a two-step approach. Okay, so carefully observe how do we calculate the conditional pattern base for A. So to get this conditional pattern basis, what you have to do is you have to follow 2 steps. What is that you have to do is It's a bigger thing. Why I didn't add a slide? I don't know. Let's carefully observe how do I construct this. Let me erase these things. So there are two steps to actually, before getting this conditional, to get this conditional pattern basis, you have two things to do. I'll let you know what are those two things. So right now everything is frequent, so I'm going to erase everything. Now the next step would be to rearrange the order of these transactions. Okay, rearrange the order of the transactions. That is what we are going to do now. Rearrange the transactions means for the transaction 1, okay, what is the item with highest frequency? B is the item with highest frequency, right? So that comes first. And what is the next? Next is D, A, D, right? A has same frequency, D has same frequency, E has same frequency. So B, A, D is the order. Okay, as B has highest frequency, it comes first. And then A has 5, D has 5, E has 5. As all the three are equal, so we just write them as is. So for transaction 2, again B, A, D, E. Okay. For transaction 3, um, what is the transaction 3? It is also BAD, right? For transaction 3 also it is BADE. What is for transaction 4? B, A, E, C. B has 6. A has 5. C has 3. So it goes to the end. E has 5. So E comes before C. What about the fifth transaction? B, A, D, E, C, right? B has 6, A has 5, D has 5, E has 5, C has 3. So C goes to the end. What is the sixth transaction? Sixth transaction is B, D, C. Okay. Now we rearranged all the transactions in the descending order. Okay. Now we construct FP tree. Okay. We construct prefix tree. Okay, this is called as prefix tree. Now we have construct prefix tree. This is becoming clumsy here, the space. So now we're trying to create the prefix tree. How do we create the prefix tree is, let me show you that in the other slide, which is important so that you can get that back. Let me add a new slide and get these things there. So the first step of this FP growth is to get the prefix tree. Okay, which is important. Let's look into. Okay, let me just take a screenshot of this so that I can go to the next slide and I'll show you how to generate the prefix tree. So let me paste it here so that I'll go show you how to generate that prefix tree. Now I got this here. These are the transactions arranged in descending order. Okay, so now let me go back, show you how to generate that prefix tree. That is simple. It's not so complex. Even every concept in this frequent pattern mining is easy. That's not so really tough. Oh God. Now I have to generate the prefix tree, right? Now the goal is to generate the prefix tree. How do I do that? These are the steps that I do. Now we are trying to generate the prefix tree. Right? This is the step. So for prefix tree, what we have to do is we have to start with the first transaction, BADE. So initially it would be pi, or else you don't really need pi as well. I'm just going to erase this. So now we will start with B. So we start with B and we go with A. The next is A. We take the first transaction, it goes from B, A, D, and E. So the count of everything will be 1, 1, 1, 1 now. Okay. So count of everything will be on top of everything we'll have null set. So BADE is the one. Now count of everything is 1, 1, 1, 1. Now the second one is BADE again. So we have that path available again. So you just have to increment the counts 2, 2, 2, 2. Okay. The third transaction is BADE. So you have that path again. So you need to increment the counts to 3, 3, 3, 3, and 3. Okay. So now we got 3 for all of this for BADE. Okay. So once that third transaction is also done, once the third transaction is also done, you will go to the fourth transaction. Okay, the third transaction is also done. Now we go back to the fourth transaction. So we are just increasing the counts as we already have this path available. We are just increasing the counts. Now go back to the fourth transaction. It is BADE. So we have BA. After A, we don't have E, right? So I extend this branch and this goes to E and C. Now we have to increase the counts. B and A before BACE is 3. Now as we have this path, I need to increment the counts to 4, right? So these 3 and 3 will become 4 and 4 now. So this 3 and become 4 and 4, and E and C came just once. So the count of them will be 1 and 1. And now then goes to BADEC. So now we have BAD. After D, you have E and C, right? After BADE, you have C. So C, you just have to extend C. Now all these counts will be incremented by 1 because initially we have 4s. Now after this, they become 5. So what does this will become now? They will become 5, 5, 4, 4, and 1, right? C is 1. So now the initial counts will get away, will get erased. So this 3 is no more valid, right? So C is no more valid. This 3 is not valid. 4 is not valid. Now, so the new counts will be 5, 5, 4, 4, 1. And now, so now we are going to do BDC, right? We don't have BDC, right? So what we are going to do is from B, we are going to extend a D and we are going to extend C. Okay. So this becomes, this 5 will become 6. So now we just need to arrange this. And now 5 becomes 6. Now 5 becomes 6, D becomes 1, and C becomes 1. So now we converted all these transactions into a prefix tree. Now this is our new prefix tree. And how does the counts look like if I want to keep this small? So it has 3 branches, B, A, D, E, C is one branch, and the counts are 1, 4, 4, 5, and 6. What is the other branch it has? The other branch it has is B. After A, we have E and C. So E, C, the counts of them is 1 and 1. Okay, that is one of the branch it has. And what is the other branch it has? The other branch it has is other branch it has is D and C. After B, it has D and C. The counts are 1 and 1. Okay. Now, uh, using this prefix tree, we are going to construct that conditional FP, right? Let me just again take this. This is how the second step. We construct this tree now, and then using this, we're going to make things a little easier. Okay. So this is the prefix tree. and I'll go back here to this page and I'll paste it here. Now we constructed that prefix tree. We got the prefix tree, right? And now from this, we will derive the conditional pattern basis. Let's look at how do we derive the conditional pattern basis for this. Okay. Again, let me this. So now we have this C as one. Now we got this prefix tree. Now we have to derive this conditional pattern basis. Okay. Again, you have to remember that this is not how you actually paste these items. Items also has to be in the descending order from the top. Okay. I mean, in the reverse order. First comes C, which is low, and then we go in the reverse order. Let me just erase this also. If I can erase this now. All right. Anyways, what I'll do right now is options. Okay, so these are no more valid. Let me just erase this. So all of these are no more valid. Okay, so the new items should be in the descending order, like C. Okay, after C we have what is the lowest. We go with E, and then we go with D. We go with A, and then you go with B. We go in the reverse order, okay, which is lower. After that we have E, D, B, A. If you even look at the prefix tree, if you go from bottom to up, it is going in the reverse order, right? After C we have E, after D, E, A, N. Now how do we construct this conditional prefixes tree is find out all the paths to C. Okay, the end item is C now. Now find out all the paths to C and give that as 1. Okay, now what I'll do is, here is one of the path. B, A, D, E is one of the path, and it is the support of C in this case is 1, right? C has support of 1. Okay, and now what is the other way? B, A, E, right? B, A, E is 1. The support is 1. And what about C? Here is also another way, BD. B, D. And there is also 1. So these paths are ending at C. BADE is one of the paths. BAD is one of the paths. BA is one of the paths. BD is one of the paths. Okay. You have got everything now. All the paths related to C. Now you are done with C. The next step is you have to find out for E now. Okay. You have to find out for E now. What is the path for what are the conditional pattern basis for E? It's the same. Let's just find out how are these ending? What are the paths that are ending to E? Now, what are the paths that are ending to E? BAD, right? BAD is ending at E, and at the support of E at that point is 4. BAD is 4. And what about BAE? E. So BAD is 1. And here is the path, right? So BA is also B comma A is also ending at 1. And so this is one of the paths, right? BA is one of the paths, BAD is one of the paths for E. What about D? D is BA4 and BA4, and what is the other one? Just B, right? Which is 1. Got it? For D, you have B, and this is one of the path. And what is for A? A for A, it is just B, 5. And for B, it is just pi. There is no way for it. So this is how you construct the conditional pattern basis from the prefix tree. It is just to find out how they are ending it. Okay, so Okay, so that is how you construct the conditional pattern basis. Wherever it is ending, just traverse that path and give the support as the end support. Whatever that is, the support is there for C, give that particular support BD is 1. So for E, where it is ending, BAD 4 and BA is 1. And for D, it is BA is equal to 4 and B is equal to 1. Here is one thing. For A, it is just B. It's the path that is available. Now once you constructed the conditional pattern basis, okay, the next step that you are going to do is constructing the conditional FP trees. Okay, the next step would be constructing the conditional FP trees. Now I just have to write all this there. Let me just do that quickly. From the conditional pattern basis, you just have to create the conditional FP trees. Okay, let me just show you how to actually do that. I'll go back to this slide and I'll start writing this. I'll start writing the same thing that we have found out there. It is C, E, D, A, B. Okay. And then conditional pattern basis is B, A, D, E at 1, B, A, D, E at 1, and then B, A is 1, B, A, E is 1, and the other one is BD is 1. Okay. BD is 1. And what about the other one? BAD is 4. BAD is 4. BA is 1. BA is 1. And the other one is BA is 4. BA is 4. And B is 1. And what about A? B is equal to 5. And this is 5. And what do we do next? How do we actually construct the conditional FP trees? Okay, that is what we will try to do that now. Now, to construct the conditional FP trees, what you have to do is find out the common items in all of this. Okay, what is common in all of this? B is common, right? Okay, B is common, A is not common, D is not common, E is not common. Only B is common, right? Okay, so how many times? You just need to increment it to 3 times. So 1 plus 1 plus 1, which is 3. Okay, so BADE will become BADE. What are the common in all these 3 things? BADE is the first one. The second one is BAE. And the third one is BD. What is common in all these 3? Only B is common. So that came 3 times. What is common in these 2? BA is common in these 2. So that becomes 5. 4 plus 1, which is 5. Okay. And now what is common in these 2? Only B, which is 5. What is common in these 2? B5, B5. Only B5 is common. Pi is pi. Okay. Now we got these items, right? Now to construct the frequent patterns, to generate the frequent patterns, what you just have to do is, this is how you generate the frequent patterns. So you just have to append C to this. So BC is one thing that you have to append. The support for this becomes 3, the same support. E has to append to BA. So from BA, what are combinations that you can generate? From BA, B, A, AB, right? So these are the three combinations that you can generate. What you have to do is just append E to the end of everything, ABE. So this generates three frequent item sets. One is BE with support of 5, AE with support of 5, and ABE with support of 5. So there is only one B, so BD, append D, and the support would become 5. And A, there is only one A, so support of that becomes 5. So these will be the frequent item sets. So this is called as FP growth. You're solving that with just using two tables. Okay. This algorithm is called as FP growth algorithm. Okay. Now the task for you is to find out when to use FP tree, FP growth, and when to use vertical approach, which is ECLAT algorithm. Just study something about it to know when to use what. Okay. Now you got the frequent item sets, right? We you from this conditional apparatus, first the first step would be just to find out the frequencies of each item, and the second thing that you have done is, what is the second thing that you have done? You have arranged them in sequential order. And the third thing is you have constructed the prefix tree. From the prefix tree, you have found out conditional pattern tree. Conditional pattern tree is nothing but find out the ways to reach C, and find out, once you found out the phase, what is the support of C will be given to this. If the support of C is 2 here, this will be 2. As this is 1, it will be 1. So that's why you have to find out all the paths to reach out to this C. BAE is the A. To reach out to this C, BD. So you got all of them. And then to reach out to E, BAD is the path. And the support for this is 4. To reach this E, BA is the path. Support for this is 1. As E is 1 here, 1. So that's how you construct a conditional pattern tree. And then conditional FP trees will be constructed by finding out the common items in all the conditional pattern bases. And you have to increment the count by summing up all the supports there. As here the support is 4 plus 1, BA is common in both of them, support will become 5. From the conditional pattern trees, you derive the frequent patterns. Okay, that is all what you have done now. And now let's quickly see, let's go back to the same patterns at item set again. Now what I'll do is I'll do the a priori algorithm on the same. Okay, let's see what happens if we do the a priori algorithm on the same. Let me just take this and do the a priori algorithm. I don't know if I have done the a priori algorithm here or not. Did I have done that? Oh, completely? Okay, let's do the a priori algorithm on this completely and see what actually happens. These are the frequent items that we have got right away. Just for a validation, I just want to validate if you have done right or not, with the right frequencies or not. So I'll take the same data set and let's apply a priori algorithm for the same data set completely. And let's see how does that look like. Okay. Now we got the result. I just want to validate the result of FP growth with the a priori algorithm. Let me quickly apply a priori algorithm on this particular item set. So let's start quickly and finish off this. So I'll start with A. What are the items that we do have? A, B, C, D, E. Okay. And now let me form this frequent item sets AB, AC, AD, AE. And this is BC, BD, BE. Right? And the next comes CD, CE, and this becomes DE. Okay, let's calculate the frequencies of AB. Frequencies of AB is 5. What about AC? AC is 2, right? AC is 2. What about AD? AD is 4, right? AD is 4. What about AE? AE is 5. What about BC? BC is 3. BD? BD is 3, 4, 5. What about BE? 1, 2, 3,
5.
5. What about CD? CD is 2. C is 2. C is 2 only, right? D 3, 4. D is 4.
4.
So now we exclude all of this. What are all that we exclude now? Something is going wrong, I think. So we need to exclude this. We need to exclude this. We need to exclude this. Okay. Now let's come back to the next combinations. Next, come back to the next combination, which is ABD, ABE, ADE. This comes BCD, BCE, BDE. Right? These are the things. Now, what is the frequency of ABD? ABD is 4. What about ABE? ABE is 5. What about ADE? ADE is 4, right? What about BCD? BCD is 2. BCE is 2. BCE is 2. What about BDE? BDE is 4. Okay. So we need to go exclude these two as well. We need to go exclude these two as well. Okay. We need to exclude these two as well. And now everything will become frequent. Now let me go back to this one. So this becomes ABDE. This becomes ABDE. ABD is also covered. It has nothing to do with this, and BD is also there. Now, what is the frequency of ABDE? ABD is 4, right? So this is 4. All right. So now what all we have got? We have got different set, which is different from what we have got before. AB5, AD4, AE5, BC3, BD5, BE5, DE4, ABD4, ABE5, ADE4, BDE4, BDE4, ABDE4. So this is all what is the right answer from a priori algorithm, right? Now why we got this? We got BC as 3, right? We got BE 5, right? We got AE 5, right? ABE 5. We got this. We got BD 5. This is also we got. We got BA 5. We got BA 5. This also we got. We missed so many stuff related to E and what we have got missed. We got missed AD4 is missed and DE is missed. DE4 is missed. ABD4 is missed. ABD4 is missed. ADE4 is missed. BDE4 is missed. ABDE4 is also missed. Okay, all of this got missed. Let's look at AD. AD. Probably we have only one way. BAD, BAC, BDC, BDC, BAEC. We got something wrong here. Let's figure out where we have missed something. That is all about a priori, I mean, FP growth algorithm. You can even give a try. The results of a priori algorithm and FP growth has to be same. Okay, we might have done something wrong there. I couldn't actually find that now. But let's go forward. Now, compact representation of frequent item sets. Now we have all this set, right? We have so much stuff present here. We have a big list of item sets that is available now. Now, is there any compact way of representing these? Do we need all these things? Is what the question now. So, do we need all of these frequent sets, or can we represent this entire set in a compact way? I mean, with less number of item sets. Is there a way to represent all of this set into a minimal set so that it would be easy to store and process? Um, so that is what we're going to study, the compact representation of the entire frequent set. One such way is maximal frequent item sets. By finding out the maximal frequent item sets, we can derive something about the frequent item sets. What can we derive and how do we derive is something that we're going to study right now. But before studying that, we just have to understand what is maximal frequent item set. A maximal frequent item set is that a frequent item set that is not a subset of any other frequent item set. Okay, a frequent item set that is not a subset of any other frequent item set. What does this mean? Just carefully observe a frequent item set that is not a subset of any other frequent item set. Okay, understood? So now go back here. This is the scatter plot. I mean, this is the lattice diagram that we have done, right? In this, what are the maximal item sets? What is maximal item set is saying? Maximal item set is saying that maximal item set is an item set for which it has no frequent, that frequent item set is not a subset of any other frequent item sets. Let's take the example. This is a frequent item set. ABD is a frequent item set, right? Okay. ABD is a frequent item set. ABD is a frequent item set, right? But is this a maximal item set? ABD is not a maximal item set because this is subset of ABD4, right? ABD is a subset of ABD4. So we have a frequent superset. Okay. If a frequent item set is called as maximal item set if it is not a subset of a frequent item set, but here ABD is a subset of this frequent item set. So now if you take ABD, is ABD is a maximal item set? Yes, ABD is a maximal item set because ABD doesn't have any, is not a subset of any of the frequent item sets, right? So it doesn't have any superset with the, which is frequent, right? ABD doesn't have any superset with the same frequent, or ABD is not a subset of any of the frequent item set. So ABD is a maximal item set. ABD is a maximal item set as it doesn't have any, it is not a subset of any of the frequent item sets. Okay, so that is the first thing. All right, so the next thing is uh, second thing is, now look at this. ABD is a subset of this. What about ABE? ABE is also a subset of ABD, so that is also not a maximal item set. Okay, that is also not in maximal item set. ABD is a subset of ABD, not a maximal. AD is also a subset of ABD, not a maximal. What about BD? BD is also a subset of ABD, so it is not. It is also not a maximal item set. What about AD? AD is a subset. AB is a subset. AE is a subset. What about BC? BC. BC is a maximal or not, maximal item set or not. BC is a maximal item set because it doesn't have any, it is not a subset of any frequent item set, right? Both the frequent item sets are not frequent. Both the supersets of BC are not frequent, right? So BC is a maximal item set. It doesn't have any superset with the, it is not a subset of any of the frequent item set. So BD is a maximal item set. Okay, BD is a maximal item set. What about BD? BD has superset, which is frequent, right? So BD is a superset of BD. So BD is not a maximal set. B is not a maximal set. It is subset of this. D is also not a maximal set. It is a subset of this. What about BD? BD is not a. So what are the, what are the maximal item sets now? A, B, D, E, and BC are the maximal item sets, right? Now what we have got? We have got A, B, D, E, and BC as the maximal item sets. Maximal item sets represented by the capital M. Now what we have got? We have got maximal item sets as, we have got maximal item sets as ABDE with ABDE, ABDE, ABDE with support 4, comma, BC with support 3. These are maximal item sets. Okay. What can we infer from this? What now this is a compact representation of what we are trying to do. For the frequent item sets, maximal item set is a compact representation. So we are representing all the frequent item sets with these two item sets. Now, what can we derive from these item sets? Okay, that is what. So we should be able to derive the other item sets also from this maximal item set, right? That is why we are calling this as compact representation. Why we are doing that is, we can conclude two things. The first thing is, maximum frequent item set efficiently summarizes patterns in large data sets. It summarizes patterns in the large data sets. We can say, what we can say about the other item sets, we can say whether a given item set is frequent or not. Given any frequent item set, by using the maximal frequent item sets, we can say the set of maximal frequent item sets, we can say that given an item set is frequent or not, but it doesn't preserve exact frequency info. We cannot say the exact support of that item set, but we can say whether that is frequent or not. That's all. That is why maximal frequent sets is called as loss information. Okay. Now let's look at that statement and understand this. What it is saying that we can say given an item set, we can say whether that is frequent or not. How can we say that that is frequent or not? We can say that by doing this. So given an item set, if AB is given to you, and if you want to find out whether that is frequent or not, what you can just do is, we just have these two item sets. This is the maximal set. Using this maximal set, we have to say whether AB is frequent or not. To do that, what you have to do is, you need to make sure this is the subset of one of the item sets in the maximal item set. If AB is subset of any of the items in the maximal item set, we can say that is frequent. If not, this will not be frequent. Okay, that much you can say. Whether given an item set, if this is frequent or not, you can say that. Let's suppose if you take AC is not the subset of any of these sets, right? ABDE or BC. AC is not a subset of ABDE or BC. So AC is not an frequent item set. So AC is not frequent. What about BC? BC is a subset of this. So you can say um, BC is a frequent item set. What about BCD? BCD is not a subset of any of this. So BCD is not frequent. What about ABD? ABD is a subset of this. So this is frequent, right? So now you are able to say whether okay. Now let's understand this. So from the maximal items, using the maximal item sets, we can say whether given an item set is frequent or not, but we cannot say the frequency, exact frequency of it, right? You cannot say that, but what you can say is the frequency of that is greater than or equal to the uh, uh, frequency of or support of the item set to which it is subset of. For example, if AB is the subset of AB4, we can say support of AB is greater than or equal to 4. Okay, which is because AB is a subset of this, so the support of AB should be greater than or equal to 4. That much you can say, but you cannot say the exact frequency. Let's suppose if you take AC is not a frequent, is not at all frequent item set, so AC is not frequent at all. Okay, if you take any other set, if you take BDE, you can say BD is frequent or not, because BD is a subset of this. So BD is frequent, and you can say the frequency of this is greater than or equal to 4, which is the frequency of ABDE. So you can say what is the minimum frequency of that particular item set, given item set, but you cannot say the exact frequency of it. That is the reason we say maximal frequent item set is a lossy summary. Okay, what it can say whether an item is frequent or not, and also the minimum frequency of it. Given an x, we can say it is frequent or not. We can say if it is frequent or not, and we can also say the support of this is greater than or equal to some m is the support of the support of the item set, maximal item set, to which x is subset of. Okay, maximal item set acts as a boundary between frequent and infrequent item sets informally. So this just acts as a boundary between frequent and infrequent items. If you draw a boundary for this is how it looks like, right? So if I draw a boundary, so this is how the boundary looks like. No, just that's wrong one. So they acts as the boundary elements. Okay, that's informal way. That's not in perfect way, but that acts as a boundary between the uh, eh, what do you say, frequent and infrequent items. So I can draw a boundary like this, right? So if I draw a boundary like this, so this is separating, right? This is I'm just drawing the boundary around frequent and infrequents. Actually, it has to go like this. Okay, so that is a boundary. That's an informal boundary. It cannot exactly specify or classify it, but that's an informal boundary of things. So this is how the boundary looks like for them. Okay, so I draw the boundary around the maximal item sets. This is the boundary. Okay, so everything below this will become infrequent. Everything below this will become infrequent, and inside this will become frequent. These are frequent and these are infrequent. Okay, so that is what boundary actually means is. So that is what maximal item sets acts as a boundary between the elements. This is all about maximal frequent item set. What we have done when we constructed maximal frequent item set means a frequent item set to which an item set is called as maximal frequent item set if it is not a subset of a frequent item set. Maximal item sets lets us know whether for a given item set, we can say using maximal item set that whether it is frequent or not. We can also specify the minimum support of that item set. So as we were not able to exactly specify the support of the given item set, we saw that we call that as lossy information because we are losing the support information of that item set. So it's a compact representation of the whole item set, whole frequent item sets. Maximal frequent item sets acts as a boundary between the frequent and infrequent item sets informally. Okay, that's all about maximal frequent item sets. Now let's understand about what is closed frequent item sets. A frequent item set that has no superset with the same support. Okay, um, with the same support. right? So now let's understand what is closed frequent item set. A frequent item set that has no superset with the same support. Okay. Closed item set is a lossless summary of the set of all possible frequent item sets. So it's saying like it's a lossless summary, it seems. Lossless summary means we should be able to say whether given an item set, we should be able to say whether that is frequent or not, and also we should be able to exactly say the support of that given item set, right? Then only it becomes lossless. If no such superset exists, like let's come back to that later. Let's find out what is the closed frequent item sets. What are called as closed frequent item sets. Okay, that is what we are going to find out now. A frequent item set is an item set that has no superset with the same support. Okay, a frequent item set that has no superset with the same support. Okay, it shouldn't have a superset with the same support. That is all it comes down to. Okay, now let's mark in this diagram. Let's mark what are uh, you know what are closed item sets. Let me draw this diagram again so that you will not feel messy. It would be real quick. Let me just take a picture and then draw it. So yeah, let me explain you what is closed item sets. We'll just I'll create a new slide for explaining that closed item set. We just have one more slide. Just bear with me for a few more minutes. With this, we will be completing item set concept completely. We have spatial item sets. I'll come back to that at the end of once we complete everything with machine learning. From Saturday onwards, we are going to start classification. We will be done with item set mining by today end of the day. I mean, I'll close that and then we can leave for the day. Let me quickly draw this diagram so that it will be easy for you. So it starts with by A, B, C, D, and E. And this goes to AB, AC, AD, AE, and this will be BC, BD, BE, and this goes to CD, CE, and DE. Okay, and now from this extension is ABD, ABE. Oh, ACD is not frequent, so AC will not come. So this comes to ADE. This is BCD is not coming. BCD is not coming. Let me write BCD. BD is not frequent. And we have BDE, which is frequent. And then we have ABDE. Okay, let me write the supports of everything. Support of this is 5, 2, 4, 5, 3, 5, 5, 2, 2, 4. ABD is 4, 5, 4, 2, 2, 4. For this it is 4. Now the main goal is to find out what we are trying to find out. We are trying to find out closed item set. What closed item set is saying that it should not have a superset with the same frequency. It doesn't bother whether it is maximum frequency or less frequency, but it shouldn't have the same frequency. Okay, that is the only catch here. A maximal item set is one where it shouldn't have a superset, frequent superset, but here it should not have the superset with the same frequency. Okay, now let's take this example AB. Okay, do AB has a superset with the same frequency? Okay, AB don't have any superset with the same frequency, right? The support of AB is 5, whereas it has supersets, but all the supersets has, this is not frequent, okay? This is not frequent. This is not frequent. This is also not frequent. This is not frequent. Rest all are frequent. Now I'm trying to find out the closed item sets now. Carefully observe. It's as simple as this. Now I'm trying to find out whether AB is closed or not. That means we already have seen closed item sets. Do you remember I of t is equal to x? Do you remember this I of t of x is equal to I of y is equal to x? This is called as closed item set. Okay, this is other way of finding it. If we don't have any frequent item sets with the same frequency, AB, this is the superset of AB, but frequency is not same. AB 4. So this is closed item set. Okay, AB is closed item set. And what about AD? AD is 4. It has superset with the same frequency, right? So AD is not closed item set. Just carefully observe this one. So AD is not a frequent item set because AD has this one with the same frequency, superset with the same frequency. For AE, it has something with the same frequency. It has superset with the same frequency. What about BC? BC. Do you have any superset with frequency for BC? No. So BC is a closed item set. So BC is a closed item set. So BC is a closed item set. Okay. What about BD? BD 5. BD with support 5. No, we don't have anything. So BD will also become closed item set. What about BE5? BD is a closed item set. What is BE5? It has superset with the same frequency. So we need to ignore that. BE is not a closed item set. What about DE? DE is not a closed item set because it has superset with the same frequency. What about BDE? BDE is also not a closed item set because it has superset with the same frequency. ADE cannot be closed item set because it has superset with the same frequency. ABE, ABE is 5, ABD is 4. So ABE is a closed item set. It doesn't have superset with the same frequency. Right? So ABE will be a closed item set. Okay. Now what about ABD? ABD is not a closed item set because it has, superset with the same frequency. ABD it has superset with the same frequency. Now ABD is a closed item set. ABD is a closed item set. ABD is a closed item set. Now if I write, the closed item set will be represented with capital C. If I write the item sets, the item sets of the closed item sets, I would say AB, BC, BD, ABE, and ABDE. Okay, ABDE. Okay, now this is the compact representation of the whole item set with the, and this is a lossless information is what they are saying. Like let's suppose write the frequencies also. AB 5, BC is 3, BD is 5, ABE is 5, and ABDE is 4. Okay, so this is a compact representation. Lossless information is what they are saying. Now let's prove that. Let's try to find out the AD, frequency of AD. Now let's find out whether AD is frequent or not, and also the frequency of AD from the closed item set. That's what we are trying to find out. Now we are trying to find out whether AD is frequent or not. Now let's find out all the item sets, closed item sets to which AD is subset of. So AD is not subset of AB, BC, BD, ADE. It's only subset of ABDE. Okay, it's only subset of ABDE. Okay, now you can say this is frequent because AD is subset of ABDE. And what is the frequency or support of this? The support of this is same as support of ABDE. Okay, support of AD will be the same as support of ABDE. Okay, which is 4. Right? Now go back to this slide. Closed item sets. Now find out this. To determine X is frequent, you can find out all the supersets of X within the closed frequent item set. Okay, you have to find out all the supersets of X in the closed frequent item sets. Okay, to find out the frequency of X. If no such supersets exists, then X is considered infrequent. If, for example, if AD don't have any superset, then AD is infrequent. Okay, AD will not be a frequent. But you know, let's suppose if it has superset, if superset do exist, X is considered frequent. Okay, superset exists if X, you would then look for the smallest support of Y of X and return frequency. That means if BE is the smallest, so support of that would be 5. Let's suppose you are trying to find out the frequency of something called as, um, let's suppose B. Okay, B is subset, B is the superset of B, B is superset of AB4, BC, B is superset of BC3, ABD, and you arrange all of them in the order, like then the smallest item set free support would be the support of B. Okay, smallest item set, that means the length of that BE has length 2, right? So that is what the smallest superset means. The frequency or the support of the item set to which you are trying to find out would be the frequency of the smallest frequent item set. So, I mean, for smallest superset of the um, item set X. That is how you calculate the, right, as it has only one superset, the support of this would become 4, which is true. Now find out AE. Now try to find out AE. What are the supersets of AE? You have only the supersets of AE is ABE and ABDE kada. So these are the supersets of AE. ABE and ADE are the supersets of AE. Now what is the smallest out of these two? ABE is the smallest. What is the frequency of it? Which is 4. What is the support of this? 5. So what is the, sorry, this is 5. This is 4. Okay. So now the smallest closed item sets frequency would be the support of this support of the item set AE. So 5 matched. That is how closed item set can represent the whole item set. From the closed item set, we can derive the support and frequency of both of them. Let's take which is not frequent, AC. AC is not subset of any of these closed item sets, so AC is infrequent. Okay, that is how you derive an item set is frequent or not from the closed item set. So if you look at this, let me write maximal item set here. What is the maximal item set that we have got? We have got ABD is the maximal item set and BC is the maximal item set. Okay, so that is the maximal item set that we have got here, right? ABD and BC. ABD and BC. So from this, what you can say, M is subset of closed item set, which is subset of item set space. Okay, you will have M subset of closed item sets. Closed item sets is subset of item set space. Okay, this is how the relation looks like. M is a lossless, is a lossy information, whereas closed item set is an lossless information. Okay, lossless summary. That is what closed item set basically means. Now coming back to the last topic, we just have 15 minutes, I think. After that, I have to join a call. Okay, let's understand what is non-derivable item set is. It's a little tricky concept, but and that is an interesting topic too. Non-derivable item set means we are not able to derive the support of an item, support of its subsets. Okay, this would be really little complex, but let me try my best to get this stuff to you. Non-derivable item sets means if the support of an item set cannot be predicted from the support of its subsets, okay, it is called as non-derivable. That means if you take this example, what is the superset in this? ABD is a superset. Okay, if we couldn't derive the support of this ABDE from its subsets, okay, if you are not able to derive the support of this ABDE from its subsets, we call that as non-derivable. Such kind of item sets is called as non-derivable. An item set is considered derivable if its support can be calculated based on the support of all its subsets. If it is not possible, it is non-derivable. It is as simple as this. Given an item set, if you are able to calculate the support of that item set using the supports of the subsets of that item set, we call that as derivable. If not, it is called as non-derivable. And what does that actually means to you is, let's try to let's try to elaborate this. Okay. Okay. Let me draw a simple diagram for you. Given a diagram, a Venn diagram, I would say. Okay. In this, I was given three transactions. Okay. Look at this similar to this. We have three transactions, three items. Okay. A, B, C. This is transactional space. Okay. Transactional space. This is product A, item A, item B, item C. What are the possible combinations from this is AB is possible, BC is possible, AC is possible, ABC is possible. So that is what you can derive from this, right? Even if you draw the scatter for this becomes ABC, AB, AC, BC, ABC, right? I'm representing this in transactional space. Why we are calling this transactional space is something that we will see. But let's understand what is A. This is the whole stuff is A, right? This is A, this is B, and this is C. What is this area called as? What is this middle area? That is ABC, right? It's part of all the ABC. What is this area? What is this area? Can I represent that as A, B, C bar? Okay. This is ABC. What is this bar? This diagram. ACB bar. This part has A and C but not B. Okay, that is what it says. A and C and not B. Okay. What about this? B A bar BC, right? Right. That is what you actually need to read. Let's suppose if I ask to write support of A, how do I write this? Support of A. How do I write support of A? Support of A can be written as like this, right? That is equal to support of A can be written as uh, I think explain something. Just give me 5 seconds. Now I'm just trying to write what is SA. SA can be written as S of AB, which is this area, plus S of AC, right? Plus S of AC minus S of ABC. Okay, just look at this. So A is summarized as what is S of A, B bar, C bar? That is nothing but this part can be represented as, just look at this. I'm drawing this. S A bar, B bar, C bar. This is nothing but part of A which is not part of B and C. So that part is this one, right? So all this is S A B bar C bar. And S of AB is nothing but this is the part. S of AB is this. Okay. Right, if you want me to take So this is S of AB. Okay, S of AB is this one, this part, and S of AC is this one, which is common for both A and C. This is S of AC. Okay, and now why we subtracted ABC? Because this middle part came twice, right? It came in here and here. That's why we subtracted it. Now, what is our goal? Our goal here is to find out the superset, the support of any of the items that can be found from its subset. Okay, that is all what you are trying to find out. Now what does that actually means here is something that you have to understand, right? Now given another item set, like um so given anything, let's suppose if you're given like this as A of B bar C bar, uh, I already told you, right? This is item set space. Okay. This is an item, this is item set space. Item set space in the sense, this is transactions, number of transactions happened here only with only item A when not B and C. Let's say the number of transactions here is 5. Number of transactions here is 2, 3. Here it is 4, 2, 1. And here none of the transactions can be 5. So that is why I called it as transactional space. Okay. Now, this is what I'm trying to convey for you. Okay, this is called as transactional space. Each of this Venn diagram, each of this item is bought, not combined with other diagram. If only A is bought 5 times, A along with B is bought 4 times, only B is bought for 2 times, only C is bought for 3 times, A and C brought together is 2 times, something of that sort. That's what you have to understand. Now, given an you want to find out the support of S, A, B bar, C bar. Okay, S A B bar C bar, in the sense this is the one, right? That is for what you are trying to find out the support of it. Now, how do you represent this? How can you remove the negotiations here? The negotiation on top of P and C. How can we get rid of these and represent them all in the positive terms? That is what you have to find out. That is called as using inclusive exclusive principle. You can do that. How can you do that is, it is as simple as that. How to write for converting this kind of functions into, now whole goal is to represent these using the supports of positive item sets. This negotiations has to be get removed so that you will convert that to positive terms, and you can actually find out the using the supports of this, you can actually find out the support of A, B bar, C bar. How do we convert these negotiations into positive terms is something that you're going to learn now. So to do this, how do you have to do is represent this in this term. Like if you take the same lattice, okay, if you take the same lattice, it started from here, right? This is ABC. Just forget about the negotiations. So here, what is the positive term? A is the positive term, BC is the negative term, right? So start from the positive term, go to the whole term. Okay, this is the lattice that you're interested in now. What you have to do is, when you are starting from the first point, give it a plus sign. Okay, give the plus sign to this. Oh, sorry. Give the plus sign to this. And for the next step, give the negative sign. And for the last step, you give the plus sign. So how do I write this is S of A minus S of AB minus S of AC plus S of ABC. Okay, this is how now a term, item set with negotiations is converted down to item sets with all the positive terms. Okay, what I have done, I have used the lattice structure, and I started from the positive term, and I went to the whole term, which is ABC, and where I have started, I have given positive to that. For the next level I have given, and for the next level I have given positive. So that becomes, I started with S of A, support of A, minus has to be applied to both the terms, minus S of AB minus S of AC plus S of ABC. Okay. So if you take the another example, if you take another example, let me take another example for you to clarify this. Okay. And let me erase all this stuff now. Now, if I want to find out, what do I like to find out now? I would like to find out the support for, okay, support for Okay, sorry about that. I thought of actually, I don't know if that comes or not. Let's find out. I would have shown you. Like, I thought, I don't think I would extend a lot more. I wouldn't be able to complete this, but let me clarify this. What I have written now, what I have found out now, I have found out for S of A, B bar, C bar, right? I have found out for S, A, B bar, and C bar. So as this is the positive term, I started from here. So what I have written for this, S of A minus S of AB minus S of AC plus S of ABC, right? So this is what we have derived. But look at this equation. Now keep S of A this side and send everything to the other side. So this becomes minus S of A becomes plus S of AB, minus S of A becomes plus S of AC. You have A, B bar, C bar here. This plus becomes minus here. So if you convert this equation to this way, S of A, keep S of A on the right hand side and move everything to the left hand side. On the left hand side, you already have A, B bar, C bar plus S of AB plus S of AC minus S of ABC. Okay. So if you look at this, both these equations are equal. Okay. So this is inclusive and exclusive principle. That's how you can derive, you can convert the negative terms to positive terms. That is what I'm trying to convey here. Now, if you want to write something like this, if you want to write something like this, let me add a new slide. I'm going to show you another example. That's what I'm trying to do here. Let me tell you this way. If you want to try to convert S, A, B bar, C, if you want to write for this, what is S, A, B bar, C? Any idea in the diagram? That this is the part, right? This is the part. S, A, B bar, C is nothing but this one. This part is called as S, A, B bar, C. This, only this part. You look at this. Don't know. Um, look at this part, something like this part. Okay, that is A, B bar, C. Now, if I want to convert these negotiations to positive terms, what the first thing that I have to do is bring all the positive terms to one side. A, C, B bar. Okay. Now, all the positive terms has to be one side and the negative term has to be one side. Now, draw the lattice again. How the lattice looks like for three variables, A, B, C. This is A, B and AC, and this becomes BC, and this becomes ABC. Okay. Now, where we have to start? We have to start from the positive term and give it a plus sign, right? Where is the positive term here? This is the positive, this is the term, positive term for us, and this is where we have to reach. So I have to give positive here and I have to give negative here. So how do I write this? This becomes S of AC minus S of ABC. Okay. So that's how we converted this function to this function. If you go back to the Venn diagram again, so this is the diagram, right? A, this is B, and this is C. A, B, C. What is A, B bar, C? I told the A, B bar, C is this part, right? A, B bar, C is this part. A, B bar, C is this part. Now, what is on the right side? This is the left hand side. What is on the right hand side says AC, S of AC minus S of ABC. What is S of AC? This is S of AC. Out of this, we are subtracting this, which is ABC. So you will get the required one. So this is how you convert a negative terms to summation of positive terms using inclusion and exclusion. Okay. So coming back to the derivation, what does that actually means is non-derivable is with a function the support of an item set cannot be derived from the support of its subsets. Okay, that's what you're just trying to convert the item sets into summation of its subsets. Okay. Now we will reach out to there shortly, but just try to understand this. Now I can represent this in this way, right? Support of any x, y bar, x is positive term, y is negative term, can be represented as for summation of for every x, which is a subset of j, which is j is uh, the one that you're trying to find out, minus 1 j modulus of j minus x support of j. Okay, I can represent this in terms of this. Let's suppose if you take the same example s of abc and apply this formula, what is the positive term here? AB. What is the negative term here? C bar. Now minus 1, what is j? J is ABC, right? Oh no, J is AB, AC. Now we are starting over here. What is the positive term? ACB bar. Sorry, this is ACB bar. So now J is AC. Okay. And what is X? X is every subset that is coming up here. So now take out this. AC J, X is every J. J is nothing but, I mean, for every J, AC and ABC will come under J. For every subset of J, take J and X. J here is AC minus X is AC. So subset is 0. So minus 1 whole to the power of 0 is 0. So that becomes support of AC plus minus 1. What is J now? J now is J now is AB ABC minus X is AC. So okay. So what is subtraction? The when you subtract this, this becomes the coordinate of that becomes 1. Minus 1 whole to the power of 1 is 1. So that becomes support of ABC. Okay. So that becomes support of AC minus 1 whole to the power of 1 is minus 1. Support of ABC. So we got the same thing. It is just applying, converting this to formula. This is an easiest way to do that. But if you want to convert this to formula, this is what you can, and I mean, it's just like alternatively, you're getting plus and minus because you will get plus and minus, you will get 1 subtracted. So all even terms will get 1 and all odd terms will get minus. So this would be the easiest way. This is the formula conversion for the same. Okay. I think that's all for today. I'll continue tomorrow. It would